Ice cream, frozen yogurt, and sorbet are engineered through precise industrial processes that transform simple ingredients into frozen perfection at massive scale. From dairy balancing and flavor formulation to pasteurization, rapid freezing, this production line reveals how sweetness and consistency are built step by step. In this documentary, we go inside modern factories to follow each mixture as it cools and sets, uncovering the science and machines that turn liquid bases into the frozen desserts everyone loves. Industrial ice cream production begins with the preparation of the liquid mix base. Raw ingredients used in the base include milk or milk solids, cream or anhydrous milk fat, sweeteners such as sucrose or glucose syrup, stabilizers, emulsifiers, and optional flavoring agents. Bulk liquid dairy components are stored in temperature-controlled stainless steel tanks connected to automated dosing lines. Milk fat content is measured using inline infrared sensors to meet formulation targets, typically between 8 and 12% depending on the product specification. Sweeteners such as granulated sugar or glucose syrup are stored in dry bins or heated tanks. Sugar is conveyed using auger screw feeders into blending tanks, while glucose syrup is pumped through jacketed pipelines at a regulated temperature between 45 and 60 degrees Celsius to maintain viscosity. Stabilizers and emulsifiers such as guar gum, mono and diglycerides, or carrageenan are added in precise quantities using dry ingredient feeders with load cell controlled hoppers. All components are blended in high capacity, jacketed stainless steel mix tanks equipped with high shear agitation. Mixing durations and shear rates are pre-programmed and adjusted based on batch size and viscosity targets. The mixture is heated uniformly to 70-85 degrees Celsius using indirect steam in the jacket to fully dissolve solids and activate emulsification agents. This thermal processing step homogenizes the mixture and ensures complete dispersion of the fat phase. The hot mix is then passed through a homogenizer at pressures ranging from 1500 to 2500 psi. This high-pressure two-stage process reduces the size of fat globules, creating a stable emulsion and improving mouthfeel and overrun stability. Homogenization is measured and recorded by inline pressure transducers and flow meters. Once homogenized, the mix is immediately cooled to below 5 degrees Celsius using plate heat exchangers. The cooled mix is transferred to aging tanks and held between 2 and 5 degrees Celsius for a period of 4 to 24 hours, depending on product type. During aging, the fat crystallizes and proteins hydrate, which enhances body, texture, and whipping properties. Aging tanks are equipped with low-speed agitators to maintain uniformity without incorporating air. After aging, the mix is pumped into continuous freezers. These machines are equipped with scraper blades and barrel chillers. The mix enters at 2 to 5 degrees Celsius and is rapidly frozen as it moves through. The freezing cylinder cooled to approximately 20 to 25 degrees Celsius using ammonia or freon-based refrigeration systems. The freezing barrel incorporates air into the mix during agitation. The amount of air added is called overrun, typically maintained between 60 and 100% by volume using controlled air injection valves synchronized with pump speed. The partially frozen ice cream exiting the continuous freezer has a temperature of 5 to 7 degrees Celsius and a semi-solid texture. From this point, the product flow diverges based on packaging format. For bulk containers, the ice cream is extruded directly into tubs or pails using piston or rotary fillers. For single-serve novelties or molded formats, the product enters downstream portioning or molding stations. In extrusion-based forming systems, the semi-solid ice cream is extruded through stainless steel nozzles onto a moving stainless steel belt, cooled to 40 degrees, using cryogenic cooling elements. The belt carries the formed shapes under a quick freeze chamber, where additional cold air is blown to firm up the shape. Inline sensors monitor form consistency and weight. Shapes are cut by ultrasonic or wire blades synchronized with belt movement. In molded systems, the ice cream is deposited into polycarbonate molds that travel on a carousel immersed in a brine solution held at 25 to 30 alcohol degrees. Product solidifies inside the mold within 8 to 12 minutes, depending on volume. Once hardened, sticks are inserted mechanically into the semi-solid mass using servo-driven arms. Demolding is achieved by briefly dipping molds into warm water baths and using pneumatic pistons to eject the bars. Fillings, inclusions, and variegates are added at multiple points. For layered products, rotary depositors add jams, caramel, or chocolate syrup between ice cream layers. Inclusion feeders dose chocolate chips, cookie pieces, or nut fragments into the flowing stream before extrusion using volumetric or gravimetric feeders. Variegates are added, using swirl nozzles or rotating spouts that inject sauces in spiral patterns into tubs. Enrobing stations apply chocolate coatings to frozen bars using curtain coaters or immersion tanks. Bars are transported on wire belts and pass through a curtain of liquid chocolate held at 30 to 35 degrees Celsius. Excess coating is blown off using air knives. Coated bars pass through a set zone where the chocolate is tempered and solidified using directed cold air streams. Toppings such as nut granules or cookie crumbs are applied to the wet coating via vibratory sprinklers before hardening. Once the shape is stabilized and the product fully frozen, packaging begins. Products are loaded into flow wrapping machines or form fill seal machines. Printed film is drawn from reels, formed around the product, and sealed using heated jaws and pressure. Modified atmosphere flushing may be applied to reduce oxygen exposure. Each package is marked with batch codes and expiry dates via inkjet or laser printers. Packaged products proceed to check weighers and metal detectors for final inspection. Weighing systems use dynamic load cells to ensure each item is within +get 1% of target weight. Metal detectors with triple coil arrays scan for ferrous, non-ferrous, and stainless steel contamination. Rejected products are removed automatically from the line and logged in the manufacturing execution system. After inspection, individual packages are sorted into multi-packs or cartons using robotic collators and carton erectors. Units are loaded into retail-ready boxes, sealed with glue or tape and labeled with barcode identifiers. Cartons are stacked by robotic palletizers into programmed patterns based on load configuration and distribution route. Stretch wrapping machines secure pallets with film before warehouse transfer. In frozen storage, pallets are maintained at 25 degrees RC or colder. Pallet locations are mapped using barcode scanners integrated into warehouse management software. Products remain in frozen inventory for no more than the shelf life period assigned to each SKU. Rotation is enforced using first expiry, first out logic based on lot and production timestamp. The entire process is supported by centralized SCADA systems that monitor temperature, viscosity, pressure, weight, flow rate, air injection volume, and cooling intensity at every stage. Each unit of ice cream is fully traceable to its ingredient lots and production conditions through digitized batch records stored in the ERP system. The production of frozen yogurt in a factory begins with the preparation of the liquid mix base, which consists of dairy solids, sweeteners, live yogurt cultures, stabilizers, emulsifiers, and water. Each component is handled in isolated supply systems to ensure batch-to-batch consistency before integration. The mix formulation is calculated to achieve a target fat content of 2 to 4%, milk solids non-fat of 8 to 12%, and a final total solids content between 30 and 38%, depending on the product type. Bulk dairy ingredients, such as skimmed milk, whole milk, and cream, are stored in stainless steel, temperature-controlled silos, or tanks, held between 1 and 4 Arlingsi. These tanks are fitted with slow-speed agitators to prevent fat separation and sedimentation. From the tanks, ingredients are drawn through dedicated pipelines with volumetric flow meters that measure and regulate dosing rates with tolerances within plus 0.2%. Sweeteners such as sucrose, glucose syrup, fructose, or high fructose corn syrup are stored in either crystalline form or heated tanks depending on their physical state. Crystalline sugars are conveyed to mixing tanks via screw feeders or pneumatic conveyors, while liquid syrups are pumped through heated, jacketed pipes to maintain constant viscosity. The addition rates of each sweetener are determined by pre-programmed recipes in the batching software and are adjusted in real time based on inline refractometers measuring total soluble solids. Stabilizers and emulsifiers such as guar gum, carrageenan, mono and diglycerides, or cellulose derivatives are pre-blended into dry mixes and introduced using vacuum powder hoppers into blending tanks containing preheated water at 60-70 degrees Celsius. This temperature is critical for full hydration and dissolution. Agitation is applied using high shear impeller mixers, ensuring uniform dispersion and hydration within 15 to 20 minutes. Viscosity is monitored continuously via inline rotational viscometers, and any deviation triggers automatic adjustment to the water feed rate or agitation speed. Once all ingredients are combined, the resulting mix is pasteurized using a continuous high-temperature, short-time HTST pasteurizer. The pasteurization process typically operates at 85 Celsius for 30 seconds to ensure microbial reduction without altering flavor or functional properties. The system includes balance tanks, timing pumps, regeneration sections, holding tubes, and cooling exchangers. Temperature probes and flow controllers verify that critical control parameters are met for every liter of mix. Any batch failing to meet time temperature integration is automatically diverted to a reject tank. Following pasteurization, the mix is homogenized in a two-stage homogenizer at pressures between 1500 and 2500 psi. The first stage breaks down fat globules to sub-micron sizes, promoting a stable emulsion, while the second stage disperses protein aggregates evenly throughout the mix. Homogenization ensures a smooth mouthfeel, prevents cream separation, and enhances the stability of the yogurt base during frozen storage. The homogenized mix is rapidly cooled to 4 degrees using a plate heat exchanger and transferred into agitated aging tanks. These stainless steel tanks have capacities ranging from 2,000 to 20,000 liters and are equipped with low-speed paddles to maintain uniform suspension without introducing air. The mix is aged for 4 to 24 hours depending on the formulation. During this aging period, fat crystallization and protein hydration take place, improving the whipping properties and final texture of the frozen yogurt. After aging, the next stage is inoculation with live yogurt cultures, a pre-prepared, freeze-dried culture blend containing specific strains of Lactobacillus, Bulgaricus, and Streptococcus thermophilus is rehydrated and activated in a sterile environment, then introduced into the aged mix in precise ratios. The inoculated mix is transferred to fermentation tanks equipped with temperature control systems. The mixture is held at 43 degrees Celsius for 4 to 6 hours, during which lactic acid is produced, reducing pH from above 6.5 to around 4.5. The acidification process causes protein coagulation, giving the base its distinctive yogurt flavor and slightly thickened texture. Once fermentation reaches the target pH, it is immediately halted by cooling the mix to below 8 degrees Celsius. This temperature shock preserves the live cultures and stabilizes the flavor. From here, the yogurt base may be held in intermediate storage for up to 24 hours before being processed further. If flavorings or colorants are required, they are added post-fermentation to preserve the viability of the live cultures. These additives are introduced through inline dosing pumps, controlled by magnetic flow meters for precise delivery. The chilled fermented yogurt mix is transferred to the continuous freezing units. These industrial freezers use scraped surface barrel designs, where the yogurt base is frozen while being continuously agitated by rotating blades. The barrel wall is chilled to between 20 and 30 degrees Celsius using ammonia or freon-based refrigeration systems. The rotating blades prevent ice crystal growth by constantly scraping the frozen layer from the barrel wall and remixing it into the semi-frozen matrix. During freezing, air is incorporated into the mix to achieve a desired overrun of 30% to 60% by volume, much lower than regular ice. Cream to maintain the dense, creamy consistency associated with frozen yogurt. The air injection rate is precisely controlled using mass flow controllers and synchronized with product flow rate. The resulting product exits the freezer at a temperature of 5 to 7 degrees Celsius and has a soft serve consistency. If inclusions such as fruit pieces, chocolate chips, or granola clusters are required, they are introduced at this stage using rotary feeders or auger-based inclusion systems. These systems are calibrated to dispense particulate matter based on mass or volume per unit of frozen yogurt. Inclusions are mixed gently into the flow using low shear blending heads to avoid damaging texture or shape. Forming and portioning depend on the packaging format. For cups and tubs, rotary or piston fillers dispense the frozen yogurt into containers on an indexed conveyor line. Fill levels are verified using laser height sensors or load cells beneath the filling stations. The containers are then lidded using pick-and-place robots, followed by heat sealing or snap lid application depending on the package design. For stick products or novelty bars, the yogurt is extruded into polycarbonate molds mounted on a carousel or linear track. The molds pass through a 30°C brine bath or air blast freezer for rapid hardening. Once the product reaches a core temperature of 18 degrees, sticks are inserted using servo-controlled plungers. The molded products are then released from the molds using brief exposure to warm water spray or ultrasonic demolding mechanisms. Products requiring enrobing are transferred to chocolate coating stations. Bars move on a mesh belt through a curtain of tempered chocolate or compound coating held at 32 to 34 degrees Celsius. Excess coating is removed using air knives, and toppings such as crushed nuts or cookie bits are sprinkled over the wet coating before it hardens in a subsequent cooling tunnel maintained at 15 degrees Celsius. Every unit, whether in cup, tub, or stick format, is passed through flow wrappers or form-fill seal machines. Packaging film is drawn over a forming collar, heat sealed along longitudinal and transverse axes, and printed with lot numbers and expiration dates using thermal inkjet systems. Products are checked on inline check weighers for mass accuracy, then metal detected using balanced coil systems capable of detecting contaminants down to 1.0 mmHg ferrous equivalents. Packaged frozen yogurt units are grouped into multi-packs or retail cartons using robotic pick-and-place systems. Cartons are sealed with hot melt glue and printed with barcodes and logistics identifiers. Palletizing robots stack cartons in programmed configurations. Each pallet is wrapped using rotary stretch wrapping machines and moved into blast freezers or deep storage warehouses. Frozen storage areas maintain air temperatures between 25 and 30 degrees Celsius, with controlled airflow to preserve texture and prevent ice recrystallization. Each pallet is tagged with barcodes that link to a warehouse management system, allowing full traceability of production date, ingredient lots, shift information, and packaging batch. The factory production of sorbet begins with the precise formulation of a base mix that typically consists of filtered water, fruit puree or juice concentrates, a combination of sugars, stabilizers, and acidulants. These ingredients are sourced in bulk and stored in isolated silos, refrigerated tanks, or powder silos based on their form and storage requirements. Before batching begins, each raw material is passed through automated intake stations where flow rate, weight, or volume is measured using mass flow meters or load cells to ensure formulation precision to the second decimal. The main batch tank is a large stainless steel jacketed vessel fitted with dual mode agitation, one high shear impeller and one slow speed anchor scraper to manage the simultaneous dispersion of powders and gentle circulation of the mix. The process begins by pumping deionized water into the tank. This water is processed through reverse osmosis filters to reduce mineral content and stabilize the flavor profile. Temperature of incoming water is held at 60 to 70 degrees Celsius to accelerate sugar dissolution and aid in the hydration of stabilizers later in the cycle. Fruit inputs, often high viscosity purees or concentrates, are pumped from cold storage tanks maintained at foreign gangs. These tanks are fitted with bottom-mounted paddle stirrers to prevent sedimentation of pulp or particulate matter. The fruit component is introduced via jacketed stainless lines with rotary lobe pumps that preserve particulate integrity and ensure steady laminar flow. Inline flow meters measure delivery in real time, adjusting valves based on programmable batch set points. Sweeteners are introduced in multiple phases depending on their type. Crystalline sugars, such as sucrose or dextrose, are stored in bulk bag unloaders and conveyed to the tank using vacuum-driven feeders or screw. Augers passing through sieve screens to remove agglomerates. Liquid sweeteners like glucose syrup or high fructose corn syrup are pumped from preheated tanks through jacketed lines at temperatures between 40 and 60 degrees Celsius to reduce viscosity. All sugar additions are monitored using an inline refractometer, which continuously reads the brix level and automatically adjusts feed rates to ensure consistency in total soluble solids. Stabilizers and emulsifiers, including locust bean gum, guar gum, or pectin blends, are pre-dispersed into a slurry using a high shear induction system connected to a secondary mixing tank. The system uses a Venturi-driven powder funnel that draws dry powders into a vortex of hot water, while shear blades break down clumps. The hydrated stabilizer solution is then metered into the primary batch tank over several minutes to allow for uniform dispersion. Viscosity is tracked by an inline rotational viscometer, while flow rate is synchronized with the agitator speed to prevent localized gelation. Acidulants are introduced once the temperature drops below 60 degrees Celsius to preserve their functional integrity. Citric acid and malic acid are most commonly used, added via microdosing pumps based on real-time pH feedback from inline probes. The typical pH target range for sorbet mix is between 3.4 and 4.2, depending on fruit type and desired tartness. Some blends may also include buffering salts or fruit-derived aromatic extracts introduced in sub-gram quantities with gear-driven precision pumps. Once the mix is fully blended, the entire volume is passed through a plate or tubular heat exchanger for pasteurization. The product is heated to between 82 and 90 degrees Celsius for a holding period of 20 to 30 seconds using a hot water loop on the heating side of the exchanger. Flow rates are calibrated to ensure that each liter achieves the required thermal profile. Temperature probes at the inlet, outlet, and holding tube ensure compliance with the time temperature curve. Any deviation from set points automatically diverts the mix to a rework tank using pneumatically controlled valves. Following pasteurization, the mix is rapidly cooled to 4 degrees Celsius using chilled glycol in the final section of the exchanger. It is then pumped to aging tanks, insulated, vertical stainless steel silos with gentle agitators. The mix is held for 4 to 24 hours, depending on stabilizer type, allowing the hydration of hydrocolloids and maturation of flavor. During aging, key metrics including bricks, viscosity, pH, and color are measured at regular intervals using inline and lab-based sampling. After aging, the mix is transferred to continuous freezers for dynamic freezing. These are horizontal barrel-type scraped surface heat exchangers with internal rotors spinning at high speed. The internal barrel is cooled by ammonia or freon-based refrigerant, keeping the wall temperature at 25 °C to 30 °C. The mix is pumped into the barrel at 4 °C and partially frozen in under 30 seconds. Rotor blades scrape frozen mix from the walls, maintaining even temperature distribution and preventing ice crystal buildup. At this stage, air is injected into the freezing chamber to achieve controlled overrun. For sorbet, overrun levels are typically between 10 and 30%, maintained using mass flow controlled air injection, synchronized with product throughput. Air pressure, temperature, and flow rate are logged continuously. The exit temperature of the product from the freezer is typically 5 °C to 7 °C, with a soft serve consistency suitable for depositing. At the point of extrusion, some product formats receive inclusions or variegates. For inclusion, dry or semi-moist elements like fruit pieces, citrus peel, or coconut shreds are fed through a belt-based dosing unit with weigh cell feedback. The feeder aligns with the product stream and deposits inclusions just before it enters the filler. Variegates, such as raspberry swirls or mango sauce, are injected via multi-nozzle swirl heads using positive displacement pumps, synchronized with container indexing to create layered or spiral visual effects. The filling system uses rotary or linear piston fillers with programmable dose volumes. Fill heads descend into the container, release the product in a bottom-up motion to prevent air entrapment, and retract at the end of the fill cycle. Laser height sensors verify the final fill level to ensure consistency. For products with decorative topping, a secondary depositor adds surface sources, fragments, or textured swirls before lidding. Filled containers are sealed with pre-cut lids or heat-sealed films. Lidding stations use servo-driven arms and apply uniform pressure to ensure adherence. Date coding and batch marking are applied using thermal inkjet or CO2 laser systems immediately after sealing. Each pack is passed through a metal detector, which uses multi-frequency coils to detect foreign metallic objects within the sealed product. Immediately post-packaging, the product enters the hardening tunnel. This is a spiral or straight belt blast freezer, where ambient air temperature is held at 35 to 45 degrees Celsius. Air is circulated at high speed to ensure fast freezing rates. Dwell time inside the tunnel ranges from 30 to 90 minutes, and the goal is to reduce the core temperature of each unit to below just 18 degrees Celsius. Faster hardening reduces ice crystal size and improves long-term texture stability. Core temperatures are verified by infrared sensors or penetrating thermocouples on randomly sampled units. Hardened products are conveyed to automated carton packers. A vision system identifies each container's orientation and positioning. Robotic arms equipped with suction grippers or mechanical clamps group units into clusters and load them into pre-erected cartons. Cartons are sealed using hot melt adhesive or tape, then labeled using a print and apply labeling system. The label includes SKU identifiers, lot number, date, and logistics barcodes. Cartons are then routed to the palletizer. Layers of cartons are stacked according to a programmed pattern to optimize pallet stability and maximize transport efficiency. Stretch wrapping machines encase each pallet in multi-layered film with preset tension profiles to secure the load during transport. Pallets are labeled with SSCC codes and sent to deep freeze storage, where ambient temperature is maintained between 25 and 30 degrees C. Storage location is recorded in a warehouse management system using RFID or barcode scanning. Each batch of sorbet is traceable through electronic production records, linking ingredient lots, formulation parameters, processing times, and packaging data. Digital records include metrics for pasteurization, bricks values, overrun, pH, freezing rate, fill weight, inclusion density, and packaging inspection results. Production lines are modular and allow for multiple flavor variants and packaging formats. Line changeovers are performed by CIP, clean-in-place cycles, product purges, and recipe uploads via the SCADA interface. Automated valves and sensor diagnostics reduce downtime between batches. Lines may produce up to 8,000 litres of finished sorbet per hour, depending on viscosity, inclusion complexity, and packaging speed. The process for Snickers peanut butter begins with the receipt and inspection of raw materials, including roasted peanuts, refined sugar, corn syrup, dextrose, hydrogenated vegetable oil, skimmed milk solids, cocoa liquor, cocoa butter, soy lecithin, salt, egg white solids, lactose, whey, and artificial flavors. Each ingredient is stored in designated silos or temperature-controlled containers depending on its physical state. Dry powders are handled in gravity-fed bins, while oils and syrups are stored in jacketed tanks with agitation and temperature control to maintain fluidity. Peanuts used in the formulation are first screened for foreign matter using rotary sieves and magnetic separators, then conveyed into buffer hoppers feeding a roller mill that cracks them into uniform granules. The granulated peanuts are then pneumatically transferred to storage silos for batch-based dispensing into the peanut butter blend. The peanut butter layer is produced in a batch mixing system where peanut granules are combined with vegetable oil, sugar, salt, and stabilizers in a ribbon blender with temperature regulation. The mixture is homogenized using a high shear inline mixer and heated to 48 to 52 degrees Celsius to achieve pumpable viscosity. The finished peanut butter is stored in jacketed holding tanks equipped with level sensors and recirculation loops to prevent phase separation. The nougat layer is prepared using a continuous aeration system. Corn syrup, sugar, and water are cooked in a steam-jacketed vessel to 120 C, 120 degrees, and transferred to an aerator, where air is whipped into the syrup, along with milk solids, egg white solids, and stabilizers. The result is a light, aerated nougat with controlled density between 0.35 and 0.45 GC/Sec-Gem3. The nougat is extruded through a calibrated nozzle system onto a continuously moving cooling belt lined with a polyethylene release film. The nougat band is cooled to below 20 degrees Celsius using overhead chillers and bottom surface cold plates. Once cooled, a uniform layer of peanut butter is deposited onto the surface using a curtain depositor. The thickness of this layer is maintained using servo-controlled doctor blades. Viscosity and temperature of the peanut butter are constantly monitored by inline viscometers and thermocouples, with feedback loops adjusting jacket temperature and pump speed. A caramel layer is prepared by cooking sugar, glucose syrup, milk solids, and fats to a target temperature of 115 to 118 degrees, followed by emulsification in a vacuum mixer to remove air bubbles. The caramel is applied as a third layer over the peanut butter using a heated roller spreader system with a calibrated gap to ensure uniform layer thickness. The caramel is cooled rapidly using forced air and chilled roller contact to reach slicing firmness. The tri-layer slab, consisting of nougat, peanut butter, and caramel, is conveyed through a compaction system consisting of top and bottom pressure belts to eliminate internal air pockets and ensure structural uniformity. The slab then enters the slitter station, where rotary knives cut it longitudinally into lanes matching the final bar width. Each blade is aligned using digital edge sensors to maintain cutting accuracy within plus or 0.5 millimeters. The individual lanes are separated using diverging conveyors and conveyed into the guillotine cutter, where servo-driven blades slice the moving slab into individual bar lengths, typically 38 to 52 grams per unit. Cut bars are spaced automatically using smart belts that adjust speed based on line accumulation to prevent product overlap and damage. Any misshaped or undersized bars are rejected using pneumatic knockoff arms. Bars proceed to the enrobing station, where they pass under a waterfall curtain of tempered milk chocolate. The chocolate is maintained at 30 BSTRs and has a viscosity range of 1,800 to 2,200 centipoise. A vibrating wire mesh belt ensures uniform base coverage, while an air knife blows off excess chocolate from the top and sides. Enrobed bars are passed through a vibrating section to settle the coating and remove trapped air. The enrobed bars enter a cooling tunnel divided into progressive zones starting at 10 degrees Celsius and gradually increasing to 16 degrees Celsius to prevent fat bloom and cracking. Tunnel length is approximately 30 to 40 meters, with dwell time ranging from 5 to 8 minutes depending on coating thickness and line speed. Product core and coating surface temperatures are measured at tunnel exit to confirm stabilization below 20 degrees Celsius. Post-cooling, bars are inspected using machine vision systems that assess enrobing quality, dimensional conformity, and surface defects such as bubbles or incomplete coverage. Rejected units are logged by defect type and removed automatically. Accepted bars continue to the packaging line, where they are fed into a flow wrapper via vibratory lanes and pocket conveyors that align them to wrapping speed. Wrapping film is fed from a roll and registered using optical mark sensors. The film is formed into a tube around each bar using a forming box. Longitudinal seams are sealed by rotary heat seal wheels, and end seals are created by jaw sealers operating at 135-150 degrees Celsius. Barcodes and date codes are printed in line using thermal transfer printers. Film tension, seal temperature, and print registration are continuously monitored by the wrapper PLC. Wrapped bars are weighed using in-motion check weighers with a resolution of 0.1 grams. Any bars outside the tolerance band are ejected using pneumatic side gates. Accepted bars are collated into groups by rotary collators and packed into folding cartons by robotic pick-and-place systems using vacuum cups. Cartons are erected, filled, and sealed with hot melt adhesive applied by contact nozzles. Cartons are verified by weight and barcode before being conveyed to case packing. Case packing involves grouping cartons into shipping cases that are erected and sealed by automated case erectors and tapers. Cases are labeled using thermal inkjet or print and apply labelers and stacked onto pallets using robotic arms with end effectors configured for the case size. Pallets are wrapped with stretch film and labeled with pallet license plates that include batch number, product code, production line, and timestamp. Finished pallets are stored in temperature-controlled warehousing environments between 18-20 C2 degrees and 50-60% RH. Warehouse management systems, WMS, use barcode scanning to log pallet locations and ensure FIFO inventory management. Distribution occurs through cold chain logistics to ensure product quality during transportation. Each process step is monitored and controlled using a supervisory control and data acquisition SCADA system that collects data from sensors, scales, thermocouples, and flow meters across all stages. This data is displayed on human-machine interfaces, HMIs, for line operators and stored in batch records for traceability. Any deviation from standard parameters triggers alarms and corrective actions. Allergen segregation protocols are enforced at every stage. Peanut and milk processing areas are physically segregated. Equipment used for peanut butter and chocolate are color-coded and cleaned separately. Swab testing for protein residues is conducted after cleaning and before changeovers. Cleaning validation includes visual inspection, chemical residue tests, and microbial swabbing. Preventive maintenance schedules for all equipment are based on run hours or production cycles. Components such as chocolate pumps, depositor nozzles, cutter blades, belt rollers, and sealing jaws are inspected and replaced as needed. Maintenance activities are logged in a computerized maintenance management system, CMMS, which alerts engineering teams when parts reach predefined wear thresholds. Quality control includes hourly sampling of bars for destructive testing. Tests include measurement of bar weight, length, width, height, chocolate shell thickness, peanut distribution, and filling ratio. Moisture content is tested using rapid moisture analyzers, while texture is measured using texture profile analysis, TPA, machines. Sensory testing is performed by trained panelists in isolated booths with controlled lighting and ventilation. Shelf life studies are conducted by storing finished products under accelerated and ambient conditions. Parameters tested include moisture migration, lipid oxidation, microbial stability, chocolate bloom, and filling separation. Results are used to validate expiration dates printed on each unit. Finished goods are subject to audit by internal QA and external certification bodies to ensure compliance with food safety standards. All production, inspection, and packaging records are stored electronically and can be retrieved instantly for traceability. Raw material lot numbers are linked to final product batch codes, allowing for upstream and downstream tracking in case of complaints or recalls. Root cause analysis is performed for any non-conformance, with results reviewed in monthly quality audits. M&M's caramel candies are manufactured through a multi-stage process that includes caramel cooking and forming, caramel center pre-coating, chocolate panning, hard shell sugar coating, polishing, sorting, inspection, and packaging. Each of these stages is optimized for continuous production and strict dimensional and weight tolerances. The process begins with preparation of the caramel center using industrial cooking vessels equipped with direct steam injection and mechanical agitation. A mixture of glucose syrup, refined white sugar, sweetened condensed milk, palm oil, emulsifiers, salt, and natural flavoring is pumped into the batch cooker. The initial ingredients are metered by mass flow meters and load cells to ensure precise ratio control, typically with a solids concentration exceeding 85% in the final cooked mass. Cooking is conducted at temperatures between 115 degrees Celsius and 120 degrees Celsius, and continuous agitation prevents scorching and ensures homogeneous heating. A vacuum step may be applied after atmospheric cooking to reduce moisture content without exceeding target temperatures, improving chew texture and shelf stability. Once the required consistency is reached, the caramel is transferred to a cooling table or cooling drum equipped with scraper arms, which reduce the mass temperature to below 50 degrees Celsius and prepare it for forming. The cooled caramel mass is sheeted and cut using a rotary cutter and high-precision die system. The sheeted caramel slab is passed through gauge rollers to reduce thickness and fed into a rotary die-cutting unit where small square or rectangular cores are punched out. The cutting system operates in synchronized alignment with the conveyor speed to avoid misshaping. Each core is formed to within plus T 0.2 mm of the target dimensions, and cut weights are maintained at 2 to 3 grams per center depending on final candy size. After cutting, the caramel centers are conveyed to a pre-coating drum where they are tumbled with a fine mist of modified starch or food-grade wax. This stage prevents sticking and prepares the surface for chocolate adhesion. The pre-coated caramel pieces are temporarily stored in stainless steel bins under humidity-controlled conditions with less than 40% RH before being transferred to the chocolate panning units. Chocolate coating is conducted in automated panning drums with oscillating movement and programmable dosing cycles. Each pan receives a calibrated quantity of caramel centers and begins rotation at 18 to 24 RPM. Tempered milk chocolate is sprayed onto the tumbling centers in controlled quantities through heated nozzles. Each chocolate application is followed by a cooling phase using dehumidified cold air injection to solidify the layer before the next application. This chocolate build-up cycle continues for multiple iterations until the centers reach the specified chocolate layer thickness. Sensors within the panning unit monitor temperature, humidity, and drum load to prevent agglomeration or flattening. The total chocolate coating phase typically lasts 60 to 90 minutes, depending on desired shell thickness and line speed. By the end of this stage, each center is fully encapsulated in chocolate and cooled to under 25 degrees Celsius before proceeding to the sugar coating line. Sugar coating, or hard panning, is performed in high-capacity rotating pans with batch sizes ranging from 300 to 600 kilograms. A mixture of sucrose, glucose syrup, water, colorant, and titanium dioxide is sprayed in layers onto the chocolate-coated centers. The initial applications are made with higher syrup content to ensure adhesion and are followed by increasingly dry applications to harden the shell. Between each application, cold air is blown into the pan to crystallize the syrup and lock the layer in place. The coating is built in 20 to 40 layers, with rotation speed, syrup flow rate, and airflow rate adjusted in real time by PLC-controlled systems. Specific gravimetric dosing pumps ensure each batch receives a uniform mass of syrup and colorant. Standard M&M's caramel products are colored using a fixed ratio of FDA-approved colorants, with pan scheduling arranged to avoid cross-color contamination. Each color batch is tracked with a unique identifier linked to its dye lot and pan ID. As the sugar shell builds, the product passes through a smoothing phase where the surface is hydrated and then gently polished with microcrystalline wax. This polishing provides the final product with its gloss and protective coating. A final tumbling phase is conducted in pans lined with polishing baffles and anti-static systems to prevent buildup on the interior walls and ensure free movement of the candies. After polishing, M&M's caramel units are conveyed to the grading station. A multi-tiered vibratory grading system separates any units that deviate from size specifications. Grading is followed by weight sorting, using high-speed check weighers capable of scanning up to 300 units per minute. Acceptable candies fall within a defined weight range. Over- and underweight items are automatically rejected and logged by defect code. Product inspection follows. Each candy passes through a vision system using a series of high-resolution cameras and 360-degree rotation to check for shell defects, discoloration, incorrect sizing, and incomplete polish. Any non-compliant unit is removed from there, streamed via pneumatic nozzles, and collected in segregated bins. Rejected items are logged and analyzed for trends in production issues, triggering upstream corrective actions if thresholds are exceeded. Accepted product is conveyed to the packaging system, where candies are temporarily stored in surge hoppers with level sensors to buffer production flow. Product is dosed using multi-head combination weighers that calculate the optimal combination of candies to achieve target package weights, typically 34 to 80 grams, depending on SKU. Weigher buckets are constructed of low-friction stainless steel and cleaned regularly to prevent flavor, carryover, or build-up. Filled product drops into vertical form-fill seal machines, where printed laminate film is formed into a pouch, filled, and sealed with constant heat seal bars. Seal integrity is verified using pressure sensors and thermographic imaging. A nitrogen flush is applied before sealing to reduce oxygen levels inside the pouch, thereby enhancing shelf life. Packages are printed with production code, best by date, line number, and timestamp using continuous inkjet printers. Sealed pouches are conveyed to check weighers for final weight verification and then pass through metal detectors set to detect ferrous, non-ferrous, and stainless steel contaminants. Any off-weight or contaminated package is rejected. Accepted packages are collated into larger trays or cartons using pick-and-place robotic arms equipped with vacuum grippers. Cartons are assembled, filled, and sealed using hot melt adhesive and barcode labels applied on the side panel. Shipping cartons are scanned and aggregated onto pallets using automatic palletizers that form specific stacking patterns for warehouse efficiency. Each pallet is wrapped with stretch film and labeled with pallet-level tracking codes tied to the plant's manufacturing execution system. Pallets are transferred to a finished goods warehouse where temperature is maintained at 18 to 20 degrees and humidity is kept under 60% RH to protect product quality. Quality assurance sampling occurs every 15 to 30 minutes at critical control points. Samples are taken from post-coating, post-polishing, and final package stages. Laboratory tests include moisture analysis via halogen, moisture analyzers, shell thickness measurement with micrometers, coating adhesion tests, drop impact testing for shell integrity, and taste panel validation. Shelf life studies are conducted on retained samples stored at standard and accelerated aging conditions. Cleaning and sanitization are conducted on a rotating schedule. Chocolate and caramel handling areas undergo full CIP, clean-in-place procedures involving hot alkaline solutions, acid rinses, and sterile water flushes. Sugar panning and polishing pans are dry cleaned using brushes, vacuum systems, and compressed air. Contact surfaces are swabbed for microbial residues, and test results are logged digitally for traceability. Allergen control is strictly enforced. Caramel and chocolate processes containing dairy and soy are segregated. Line clearance protocols require full removal of previous ingredients, verified by visual inspection and protein swab testing before new production begins. Changeovers are validated with QA sign-off. Batch tracking is implemented through digital batch records containing ingredient lots, process parameters, equipment settings, cleaning records, operator IDs, inspection results, and deviation logs. Any deviation from specification limits requires root cause analysis and corrective action under documented quality systems. Rework from rejected product is limited and processed only after evaluation of safety and quality impact. Preventive maintenance occurs based on machine runtime hours. Key systems like chocolate pumps, coating nozzles, panning motors, weighing buckets, and forming jaws are monitored for wear and replaced proactively. Predictive diagnostics include vibration analysis and temperature monitoring of motor bearings, and these readings are stored in a central database for long-term equipment performance tracking. The production of Twix White begins with the synchronized preparation of three main structural components: the shortbread biscuit base, the caramel layer, and the white chocolate coating. Each component is manufactured in separate sublines within the facility and converges later during the bar forming phase. The process starts with the biscuit base. Refined wheat flour, invert sugar syrup, vegetable shortening, powdered milk, salt, and leavening agents are dispensed into a horizontal planetary mixer. Dry ingredients are fed from bulk storage silos through gravity chutes or pneumatic lines, each portion controlled by weigh batches to an accuracy of plus 1%. Liquid components are pumped from heated jacketed tanks and injected through metered valves. The mixing cycle includes 2 stages: dry blending for even distribution of powders, followed by wet incorporation using medium speed agitation. The dough is formed to a target moisture content between 16 to 18% to ensure optimal flow and shaping characteristics. Upon completion, the dough is conveyed via a stainless steel auger system to a rotary molder. In the rotary molding station, the dough is formed into uniform, rectangular shortbread fingers. The molder consists of a rotating drum engraved with bar-shaped cavities and a compression roller. Dough is pressed into these cavities as the drum rotates over a steel forming plate. Excess dough is scraped off by a doctor blade and recirculated back into the feed system. The molded dough pieces drop onto a perforated baking belt made of food-grade stainless steel mesh. The formed biscuit bases enter a continuous tunnel oven with multiple heating zones. Each zone uses indirect gas-fired heat or electric radiant panels to maintain a gradient from 180 degrees Celsius at the entrance to 220 degrees Celsius in the final zones. The baking time ranges between 8 to 10 minutes. Infrared sensors monitor surface temperatures, while dew point sensors control internal humidity. The goal is to fully gelatinize the starch, set the structure, and reduce internal moisture content to below 3.5%. After baking, the biscuits are transferred to a mesh cooling conveyor where ambient air is forced from both above and below using axial fans. Surface temperature is reduced to under 30 degrees before the biscuits are sent downstream. During this phase, any misshaped or cracked bases are automatically rejected using laser sensors and high-speed diverters. Parallel to biscuit preparation, caramel is cooked in a steam-jacketed stainless steel cooker equipped with a vacuum system. The caramel mixture consists of glucose syrup, refined sugar, sweetened condensed milk, vegetable fat, and emulsifiers. The blend is heated to between 115 degrees Celsius and 120 degrees Celsius under continuous agitation to achieve a homogeneous, smooth consistency. A vacuum stage follows to reduce moisture content and prevent Maillard browning beyond the desired level. Once cooked, the caramel is pumped through an inline cooler, reducing its temperature to 50 to 55 degrees Celsius and fed into a pressurized buffer tank. The caramel is held under constant agitation to prevent crystallization and separation. It is then transferred to a curtain depositor located above the biscuit lines. Each biscuit base moves underneath the depositor at synchronized speeds, where a layer of caramel approximately 3 to 5 mm thick is dispensed onto the center. The caramel-coated biscuits proceed to the chilling tunnel, which operates between 5 degrees Celsius and 8 degrees Celsius, with controlled air velocity and laminar flow. This section ensures the caramel firms to a semi-solid state, allowing the bars to retain shape during subsequent handling. Cooling dwell time is carefully controlled to prevent cracking or internal condensation. Next is the enrobing process. White chocolate coating is prepared by melting white compound chocolate composed of sugar, milk solids, cocoa butter alternatives, and lecithin. It is stored in heated tanks, maintained at 42-45 degrees Celsius. The chocolate is filtered to remove particulate matter and pumped into the enrober. Each caramel-topped biscuit is conveyed through a waterfall curtain of white chocolate. The enrober consists of a chocolate pump, curtain plate, bottoming pan, and vibrating removal section. The base of each bar contacts a submersion roller to ensure full underside coverage. A vibrating wire belt helps distribute the chocolate evenly, while an air knife system positioned immediately after the curtain blows excess chocolate off the top and sides to maintain uniform shell thickness. The enrobed bars enter a cooling tunnel set to 10 to 14 degrees. The tunnel is 20 to 30 meters long and provides 3 and 6 minutes of cooling time. The goal is to solidify the chocolate coating to a firm, glossy finish without causing thermal shock or shell fractures. Airflow patterns and tunnel humidity are tightly regulated to prevent surface bloom and condensation. Upon exit, bars pass through a vision inspection system. High-resolution cameras capture top, side, and bottom views. Pattern recognition software detects coating voids, caramel leaks, surface cracks, and dimensional anomalies. Bars not conforming to target specifications are removed via pneumatically controlled ejectors and collected in reject bins for offline evaluation. Compliant bars are transferred to the primary packaging line. Bars are individually flow wrapped using printed multi-layer laminate films. The film is drawn over a forming collar and sealed using horizontal sealing jaws, operating at 135-145 degrees C. Before the end seal is applied, a nitrogen flush displaces oxygen within the wrapper to preserve product freshness and extend shelf life. A thermal inkjet printer marks each wrapper with a date code, lot number, and timestamp synchronized with the manufacturing execution system. Sealed bars are conveyed through metal detectors calibrated for stainless steel and ferrous particles at sensitivities below 1.5 ppm. Packages outside weight or contaminant parameters are ejected and logged. Wrapped units are collected into collators that form groups for secondary packaging. Robotic pick-and-place systems use vacuum grippers to load bars into pre-formed cartons or trays. Cartons are closed using hot melt glue, and barcodes are printed for traceability. Completed cartons are conveyed to automated case packers. Shipping cases are assembled, filled, and sealed using tape or adhesive. Each case is labeled with a shipping code, pallet code, and production metadata. Palletizing robots stack cases according to predefined patterns. Pallets are stretch wrapped and scanned before being stored in the finished goods warehouse, which maintains ambient temperatures of 18 to 20 degrees and relative humidity under 60%. Each bar produced is tied to a batch number through digital production records, including all ingredient lot numbers, mixing parameters, baking temperatures, caramel cooking data, enrobing flow rates, cooling dwell times, and packaging specifications. These records are accessible for traceability, audits, and regulatory compliance. Routine inline quality control includes sampling from every production hour. Samples are weighed, measured, and evaluated for coating thickness, layer adhesion, caramel placement, and hardness using calibrated micrometers and texture analyzers. Moisture content is verified using halogen moisture balancers, and chocolate temper is tested with temper meters to confirm crystallization profiles. Laboratory testing also includes water activity analysis, fat bloom resistance, and accelerated shelf life testing under elevated temperature and humidity conditions. Results are logged in a quality database and reviewed by technical managers during shift changes and weekly audits. Sanitation of the line is scheduled daily and weekly depending on the zone. Dry cleaning is applied to the biscuit molding and baking lines using brushes and compressed air. Wet cleaning is used on caramel and chocolate zones, involving hot water rinses, food-safe alkaline detergents, acid neutralizers, and sanitizer sprays. Enrober parts are disassembled and cleaned using CIP-compatible tanks. Allergen management involves physical segregation of peanut, tree nut, and dairy-containing ingredients. Changeovers require full clean-out of product contact surfaces and verification using allergen-specific protein swab kits. If protein residue exceeds defined thresholds, equipment is re-cleaned until test values fall within limits. All material movement, from raw ingredient delivery to palletized product dispatch, is tracked using barcodes and integrated into the facility's ERP and SCADA systems. These systems enable real-time monitoring of production rates, downtime, line efficiency, scrap rates, and output per shift. Alarm logs, deviation reports, and maintenance requests are automatically archived for compliance purposes. Preventive maintenance schedules cover all rotating equipment, pumps, cooling compressors, depositor heads, vibratory conveyors, belt motors, and sealing modules. Wear parts such as blades, nozzles, bearings, belts, and gaskets are replaced at specified run-hour intervals. Predictive analytics using vibration sensors and thermal imaging assist in identifying failure risks before downtime occurs. The process begins with the preparation of the core ingredient, the peanut butter filling. Whole, dry roasted peanuts are delivered in bulk to the facility. These peanuts first enter a vibrating conveyor that removes loose skins and broken fragments. they pass under a high-powered magnet to eliminate any residual metallic particles. Then, the peanuts are gravity-fed into a stainless steel grinding chamber. Inside, large rotating blades crush the peanuts under high torque. The first grind reduces them to a coarse paste, maintaining some granular texture for mouthfeel. The paste is then pumped into a second stage grinder, equipped with finer burrs, reducing the particle size to below 20 microns. During this stage, a metered flow of salt, sugar, and hydrogenated vegetable oil is introduced via precision-controlled valves, ensuring consistent viscosity and sweetness across all batches. The resulting emulsion is routed through a jacketed pipe system, maintained at a specific temperature to keep the filling fluid enough for metering. This peanut butter flows into a holding tank fitted with an agitator that constantly stirs the mixture to prevent separation. The tank is linked to a high-speed depositor, which measures and dispenses precise volumes of the filling for the next stage. However, before the filling is used, the outer shell of the cup must be created. The outer chocolate coating begins with the mixing of ingredients: chocolate liquor, cocoa butter, milk solids, and sugar. These ingredients are loaded into a large-scale conche, a machine with heavy rollers that knead the mixture continuously for up to 12 hours. The conching process smooths out the texture and volatilizes undesirable flavors. After conching, the chocolate is pumped through a series of heated pipelines into a tempering unit. This unit cycles the chocolate through controlled heating and cooling zones to encourage the formation of stable cocoa butter crystals. This tempering process is crucial for creating a glossy finish and a crisp snap in the final product. Tempered chocolate is then delivered into the cup forming system. Small polycarbonate molds, arranged in a continuous chain, move along a conveyor. At the first station, the molds are vibrated to eliminate air and then receive a precise amount of tempered chocolate. The molds pass beneath a rotary spinning unit that evenly distributes the chocolate along the interior walls, forming the shell. Rapid air jets cool and solidify the shell as it moves to the next station. Once the shell is set, the molds proceed to the filling line. Here, servo-controlled nozzles descend into each chocolate cavity and inject a precise volume of peanut butter filling. The temperature and flow rate are tightly regulated to ensure smooth deposition without overflow or disruption to the shell's integrity. As the filling sets, the molds continue moving to the capping station. At the capping station, a second layer of tempered chocolate is applied over the exposed filling to seal the cup. A gentle vibration removes trapped air and levels the surface. The molds then enter a refrigerated tunnel where they spend several minutes at sub-zero temperatures. This rapid cooling locks the structure in place and allows for demolding without cracking or warping. After cooling, the mold chain reaches the demolding station. A synchronized pusher mechanism nudges each mini cup out of its cavity. The cups drop onto a soft conveyor belt lined with food-grade cushioning material. From here, they are directed to an inspection line equipped with high-resolution cameras. These cameras scan each unit for surface defects, incorrect shape, or incomplete sealing. Any product that falls outside tolerance is automatically ejected via an air jet mechanism. Perfect cups continue along the belt to the wrapping system. The cups pass through a vibratory feeder that aligns them uniformly before entering the wrapping carousel. Here, pre-cut foil wrappers are fed from a roll and precisely positioned. A series of rotating arms wrap the foil around each mini, folding it into the familiar pleated skirt pattern. Heat-sensitive adhesives are applied in microdots to secure the foil in place without melting the chocolate underneath. The wrapped minis are then transferred to a bucket conveyor, which lifts them vertically to the weighing and portioning unit. This section uses a combination of multi-head weighers and vibration channels. Each head calculates the exact weight of its portion and releases it into a funnel only when the total matches the predefined package weight. The minis fall into open pouches below, which are already held in place by a form-fill-seal machine. As each pouch is filled, it moves to the sealing station. The top edges are pressed together between heated jaws that apply pressure and temperature simultaneously, creating an airtight seal. Excess air is evacuated prior to sealing to prevent bloating and ensure compact packaging. After sealing, each pouch is marked with a lot code and timestamp using a thermal inkjet printer for traceability. The sealed pouches drop onto a short accumulation conveyor that buffers the output before transferring them to a final packing station. Here, robotic arms pick up the pouches and place them into pre-formed cartons with precise orientation. The cartons are closed, sealed with hot melt adhesive, and stacked in layers onto shipping pallets using a gantry-style palletizer. Each completed pallet is automatically stretch-wrapped for stability and sent to storage for distribution. This entire process is governed by a centralized control system that monitors temperature, humidity, belt speed, deposition volumes, and flow rates. Real-time sensors feed data to a control panel, allowing technicians to make micro-adjustments and ensure batch-to-batch consistency. The system can run continuously for up to 24 hours without stoppage, capable of producing tens of thousands of minis per hour. Next, the focus turns to how raw materials are handled before entering production. Peanuts arrive in bulk tankers and are gravity discharged into underground silos lined with food-grade epoxy. Each silo is equipped with aeration systems to prevent moisture accumulation and ensure uniform temperature. The peanuts are pneumatically conveyed through stainless steel tubing into a vibratory feeder that meters the flow into a destining machine. This device uses oscillation and airflow to separate stones, soil particles, and foreign debris from the peanut stream. From there, the peanuts pass through a laser optical sorter that uses infrared and visible spectrum imaging to detect discolored or malformed nuts. High-speed air nozzles eject any flawed peanuts in milliseconds. Only uniform, high-grade peanuts proceed to the roasting unit. This unit is a continuous belt roaster with adjustable zones. Peanuts pass through multiple chambers where hot, dry air is circulated by impeller fans. Temperatures are carefully staged, rising from 120 to over 160 degrees Celsius, which drives out moisture and enhances flavor through Maillard reactions. Once roasted, the peanuts are cooled, using forced ambient air passed through a vibrating bed. This prevents residual heat from continuing the roast and ensures a consistent final color and texture. The roasted peanuts are then fed through a skin removal drum that uses abrasion and airflow to strip the outer skins. The clean peanuts are conveyed via vacuum lift to the grinding area, where the previously mentioned multi-stage grinding begins. Simultaneously, chocolate ingredients are stored in segregated silos and tanks. Sugar is kept in dehumidified environments to prevent caking. Milk solids and cocoa powder are transferred via screw augers into premix hoppers. Cocoa butter and chocolate liquor are maintained in heated jacketed tanks to remain fluid. All ingredients are automatically metered and conveyed to the conche for blending. The chocolate mass, after completing the conching phase, enters a holding tank fitted with constant agitation paddles to maintain homogeneity. From there, it's pumped into a multi-stage tempering system composed of a series of heat exchangers and temperature control zones. The chocolate is first heated to melt any remaining crystals, then rapidly cooled to initiate the formation of stable crystal forms, and finally brought back to a processing temperature that maintains its tempered state. This temperature is precisely held between 30 and 32 degrees Celsius, depending on the chocolate formulation. This tempered chocolate flows directly into a reservoir connected to the cup-forming depositor. This depositor features a rotating drum fitted with piston cylinders, each calibrated to dispense exact volumes of chocolate into the molds. As each polycarbonate mold tray moves beneath the depositor, the nozzles descend and fill each cavity with a metered dose. Immediately after deposition, the molds enter a vibrating station. Here, high-frequency vibrations cause the chocolate to flow evenly into the intricate cup recess, eliminating trapped air bubbles and ensuring the chocolate climbs uniformly up the sides. Next, the molds travel through a cooling tunnel set to gradually decrease the temperature. The tunnel is segmented into thermal zones that first solidify the outer edges of the chocolate shell and then slowly cool the entire form to prevent cracking. The movement through the tunnel is continuous and synchronized, with the chocolate shells emerging after a calculated duration with fully formed, hardened interiors. At this point, the molds reach the peanut butter filling station. A separate heated pipe system maintains the filling's viscosity, keeping it soft enough to flow but not hot enough to melt the chocolate shell. This balance is crucial. The filling enters a pressurized manifold, which feeds into a multi-head depositor equipped with servo motors. Each head aligns perfectly with the center of the chocolate shells and injects the filling with millisecond precision. The volume of filling is less than the total cavity depth, leaving room for the chocolate cap that will follow. As soon as the peanut butter is deposited, the mold trays pause momentarily while a burst of cool air is blown across their surface. This quick setting step helps firm up the top surface of the filling, preparing it for the capping stage without blending into the final chocolate layer. The capping process begins as the molds continue along a conveyor that passes beneath a second chocolate depositor. This unit mirrors the cup-forming depositor in design, but delivers a thinner stream of chocolate, just enough to create a smooth, flush surface over the peanut butter. The moment the cap is applied, the trays enter a second cooling tunnel with slightly lower humidity and temperature levels. This cooling tunnel runs longer than the first, allowing the entire assembly, base shell, filling, and cap, to solidify into a single bonded unit. Once fully cooled, the molded cups must be extracted without damaging their structure. At the demolding station, each polycarbonate tray is inverted over a soft silicone belt. Pneumatic actuators positioned above each cavity deliver a gentle burst of compressed air to eject the cups downward. The silicone belt cushions the fall and conveys the cups to a visual inspection zone. This inspection zone features an array of high-speed cameras positioned at multiple angles. Each cup is rotated in place as cameras scan for surface imperfections, discoloration, uneven capping, or malformed shapes. The system uses real-time image recognition algorithms to detect defects within milliseconds. If a unit fails inspection, it is marked by a food-safe dye jet and then removed further down the line by a robotic picker. Passing the inspection, the cups proceed into the foil wrapping module. The cups are gently aligned by centrifugal force in a rotating disc feeder. As each cup enters the wrapping station, it passes through a timing screw that spaces them evenly. Each cup is paired with a pre-cut foil sheet fed from a stacker. A vacuum arm lifts the foil and places it atop the cup just before it enters the wrapping drum. The wrapping drum rotates at high speed. As the cup and foil pass through its internal channels, shaped mandrels fold the foil around the cup. Fine-toothed wheels pleat the edges in the signature ruffled pattern. During this rotation, a micro dot of adhesive is applied to the final fold, locking the wrap in place. The entire wrapping process takes less than 1 second per unit, with the machine capable of processing several hundred cups per minute. After wrapping, the minis exit onto a multi-lane conveyor. These lanes gradually converge into a single stream, where the minis fall into a vibratory channel that leads them to the multi-head weigher. This weigher consists of a circular array of hoppers, each continuously filled with minis. Load cells beneath each hopper constantly monitor the weight. The system's algorithm selects a combination of hoppers that together match the target pouch weight most precisely. Once the optimal combination is determined, the corresponding hoppers release their contents into a chute, which guides the minis into the waiting pouch below. The pouch is held open by mechanical grippers in a vertical form-fill seal machine. This machine forms the pouch from a continuous roll of pre-printed laminate film. As the film unwinds, it passes through a forming collar that folds it into a tube. Vertical heat seal jaws bond the overlapping edges of the tube, while horizontal jaws seal the bottom to create the pouch base. The minis are then dropped into the open pouch, and the top is sealed immediately after filling. The sealing jaws apply precise heat and pressure, creating a strong, airtight bond. After sealing, each pouch travels under a printer head that marks it with production data, including time, date, and batch identification code. These markings are made using thermal inkjet or laser etching systems, depending on the packaging material. The printed pouch then passes through a final check weigher to confirm the net content. If underweight or overweight, the pouch is automatically diverted to a reject bin. The verified pouches proceed to the cartoning area. Here, a carton erector unfolds flat cardboard blanks and seals the bottom flaps with hot melt adhesive. Thus, open cartons are then conveyed to an indexing station, where robotic arms pick the filled pouches using vacuum grippers. These robots operate with vision guidance, ensuring the pouches are oriented correctly before placement. Each carton receives a set number of pouches, after which the top flaps are closed and sealed. Cartons then travel to the case packing area. Another robotic system groups the cartons into layers and places them into corrugated shipping cases. Each case is automatically labeled with barcodes and stacking instructions. Finally, the loaded cases are conveyed to the palletizing cell. Here, a 6-axis robotic arm equipped with suction cups lifts each case and arranges them on a wooden pallet in a tightly packed configuration. The completed pallet is wrapped with a stretch film using a rotating arm wrapper. This layer of plastic holds the cases together for transport, protecting them from moisture and movement. The entire pallet is then scanned for load integrity before being conveyed to the staging area, awaiting dispatch to distribution centers. All this activity is coordinated by a central manufacturing execution system. The MS tracks every movement and status of the materials, from peanut intake to finished carton. It interfaces with programmable logic controllers on the production floor to dynamically adjust machine settings based on real-time feedback. For example, if a slight shift in chocolate viscosity is detected, the MES can command the tempering unit to fine-tune the temperature curve. Similarly, if the peanut butter depositor records a higher than average flow rate, the filling head's piston stroke is automatically adjusted to compensate. Material traceability is ensured by RFID tagged ingredient containers and barcode scanned intermediate products. This allows every peanut butter cup mini to be traced back to the exact raw material batch it came from. Sensors track humidity and temperature at every stage, particularly within the cooling tunnels and storage silos. Even foil wrappers are logged and matched with machine lot codes. Automation is layered at every level. Pick-and-place robots replace manual handling. Vision systems eliminate the need for human inspection. Real-time analytics optimize yield and reduce waste. Redundant systems ensure that any malfunction is isolated without halting the entire line. Conveyor speeds are synchronized across zones to maintain timing continuity. The packaging line continues with precise, timed coordination as the sealed cartons are conveyed toward the aggregation system. This system groups multiple cartons into defined sets according to the final pallet configuration. A servo-controlled diverter arm separates cartons into staging lanes. Once the predefined group is complete, often in rows of 6, 8, or 12, an overhead gantry equipped with vacuum suction heads lowers onto the group, lifts the entire set, and places it into a corrugated master case. This movement is completed in a single fluid action to minimize cycle time. Before the master case is sealed, a leaflet or folded instruction insert, used for some international markets, is dropped into the case by a pneumatic feeder. The flaps of the case are then closed and sealed with twin hot melt glue nozzles, precisely depositing adhesive in a consistent bead along the contact edges. Immediately after the flaps are compressed shut, a set of pressure rollers moves over the top of the case to ensure uniform adhesion. Next, the sealed master case is conveyed under an inline labeling system. Here, a thermal transfer printer produces large format labels containing product SKUs, batch codes, barcodes, and destination identifiers. An applicator arm synchronizes with the moving case, slapping the printed label onto the side panel without stopping the line. A high-resolution camera follows, verifying that each label is present, legible, and properly aligned. If the label is missing or unreadable, the case is automatically diverted into a correction lane where a manual relabeling station awaits. From there, the master cases move toward the palletizing station. Palletizing begins with empty wooden pallets being fed from a stacker. An automatic destacker lowers and releases a pallet onto the loading zone. A vision-guided robotic arm reads the barcodes on incoming cases to determine their orientation and designated location on the pallet. Each case is picked up with a vacuum gripper or clamp-style end effector and rotated, if necessary, to match the programmed stacking pattern. Cases are placed in interlocked layers, alternating orientation by row to increase structural stability. As each layer is completed, a slip sheet is dispensed from a vertical magazine and dropped onto the layer before the next row begins. This adds friction between layers and protects the contents from compression. When the pallet reaches its full load height, typically 6 to 8 layers, the robotic arm disengages, and the loaded pallet is conveyed to the wrapping station. At the wrapping station, the pallet is rotated on a turntable while a film carriage ascends and descends, dispensing stretch film under tension. The film is pre-stretched using powered rollers to increase load stability without using excess material. Once wrapping is complete, the film is cut and sealed using a heat blade, and a final top sheet of film is applied to provide dust and moisture protection. A cornerboard dispenser may apply vertical reinforcements along the pallet edges if required for export shipping. After wrapping, each pallet is routed through a check-in station equipped with RFID scanners and weight sensors. The data collected here is sent to the factory's logistics system, which assigns the pallet a dock number and dispatch order. Automated guided vehicles or laser-guided forklifts transport the pallet from the end of the line to the designated outbound dock. This end-of-line logistics system integrates seamlessly with upstream production data, allowing full visibility and traceability from raw ingredients to finished pallet. The factory's architecture is designed for just-in-time flow, meaning there is minimal buffer storage between stages. The speed and precision of every downstream step are tightly dependent on the upstream processes delivering product at the correct pace. Meanwhile, upstream processes like ingredient blending and chocolate tempering continue in a closed loop. The chocolate mass in the tempering unit is constantly monitored by inline viscometers and refractometers. These instruments send live data to the automated control system, which modulates the heating and cooling stages to keep the chocolate in its stable crystalline form. Any deviation in viscosity or temperature is corrected in real time by adjusting the flow of chilled or heated glycol in the jacketed lines. The peanut butter filling line operates on a similar control philosophy. The filling's consistency is maintained within strict tolerances using shear rate sensors and pressure transducers embedded in the deposit line. If a slight thickening is detected, a micro amount of vegetable oil is introduced upstream at the blending tank, rebalancing the emulsion. These corrections are automated and occur without interrupting production. To ensure continuous supply, the system uses dual tanks for both chocolate and peanut butter. While one tank feeds the depositor, the second is cleaned, refilled, or brought up to processing temperature. This tank switching sequence is managed by a series of automated valves and level sensors. When the active tank nears depletion, the system seamlessly switches to the secondary tank, ensuring an uninterrupted flow to the depositor heads. The mold handling system is another key area of automation. Molds are part of a closed-loop carousel that runs on synchronized drives and encoders. Each mold is equipped with an RFID chip embedded in its frame. This allows the system to track the position and status of every individual mold, whether it is empty, partially filled, cooling, or at the demolding stage. If any mold is flagged as defective, it is automatically diverted to a cleaning and inspection loop where high-pressure water jets and ultrasonic baths clean the mold before it re-enters production. The cleaning systems themselves operate on fixed intervals. Chocolate contact lines are flushed with a food-safe solvent followed by hot water, then dried with filtered air. The peanut butter system undergoes a similar process, but also includes pigging, a technique where a cylindrical plug is pushed through the pipe to scrape residual filling. This ensures complete evacuation of material between batches and prevents buildup that could interfere with flow or hygiene. Another critical area is temperature management. Chocolate, peanut butter, and the air in various tunnels must be tightly controlled. The cooling tunnels operate with precision climate control using chilled glycol coils and air recirculation fans. The air inside each tunnel is filtered and dried to prevent condensation from forming on the cooling surfaces. Each tunnel is divided into zones, and the temperature in each is independently adjustable. This allows the product to be gradually cooled in stages, minimizing thermal shock and maintaining product integrity. The wrapping foil is also treated as a critical input. Foil rolls are stored in a humidity-controlled chamber and automatically loaded into the wrapping machines by robotic arms. Before entering the wrapping system, each roll is scanned with a spectrometer to verify that the foil's thickness, reflectivity, and coating align with specifications. Foil with even slight variations in thickness can cause machine misfeeds or affect the aesthetic of the final wrap. Every component, from the ingredient to the final unit, is integrated into a massive data collection system. Thousands of sensors measuring temperature, pressure, weight, viscosity, and speed generate real-time data that feeds into a plant-wide dashboard. This dashboard is monitored by a centralized control room that receives live alerts, trend reports, and predictive maintenance warnings. If a chocolate depositor starts running slightly slower than average, the system calculates whether this indicates wear on a motor, blockage in a pipe, or fluctuation in chocolate viscosity. A maintenance ticket is generated automatically, allowing for preemptive servicing before failure occurs. The same predictive logic applies to wear-prone parts like the foil wrapping mandrels, depositor pistons, or vacuum grippers. Cycle counts are tracked, and components are retired or serviced according to usage thresholds. This predictive maintenance ensures that the machines run at optimal efficiency with minimal unplanned downtime. Air quality within the production zone is also tightly regulated. The environment is filtered using HEPA-level air handling units that remove particulates and microorganisms. Positive pressure is maintained in clean zones to prevent contamination from adjacent areas. Even the flow of personnel and carts is controlled via airlock-style entry points and floor-level pressure mats that trigger sanitation protocols. The factory operates in a rhythm of continuous throughput. Each component, chocolate mass, peanut butter filling, molds, wrappers, pouches, cartons, pallets, flows through its respective subsystem at precisely regulated speed. The coordination of these movements relies not only on mechanical timing, but also on software orchestration. The entire plant is governed by a hierarchy of control. Field-level PLCs manage individual machines, line controllers handle sequences of machines, and supervisory control software integrates everything into a single process flow. Oreo wafer rolls are produced using a dual-stream manufacturing process involving continuous wafer sheet production and separate cream filling preparation, which are later synchronized through an automated integration line. The raw materials for the wafer component are dosed automatically from bulk silos into individual weighing hoppers. The base formulation consists of low-protein wheat flour, high-fat alkalized cocoa powder, refined sucrose, leavening agents, salt, water, and a controlled amount of oil-based emulsifiers. Dry ingredients are metered into a high-capacity horizontal mixer with dual-axis paddles designed for uniform blending. Liquids are injected through precision nozzles mounted at the top of the mixing chamber. The total mixing cycle is programmed between 6 and 8 minutes at varying RPMs, first for dry distribution, then for incorporation of wet components. Dough temperature is maintained between 22 and 26 degrees Celsius. Moisture content is monitored via inline near-infrared sensors and must fall within 10.0 to 11.5% before release to the forming line. Dough is transferred via a covered screw conveyor to a pre-sheeting station. Here, a primary roller flattens the dough into a rough sheet approximately 5 mm thick, which then feeds into a 3-stage reduction system. Each stage includes a pair of high-precision, counter-rotating steel rollers with micrometric gap control that sequentially reduce the dough thickness to 1.2 pounds. Dough tension is maintained using differential speed rollers to avoid tearing. Edges are trimmed continuously using rotary cutters, and trimmings are conveyed pneumatically back to the pre-mix hopper for reintegration. The thin dough sheet enters a continuous baking tunnel consisting of 8 to 12 independently controlled zones. Heating is achieved via direct gas-fired convection and radiant ceramic panels. Internal zone temperatures range from 180 to 220 degrees Celsius depending on the position. Air velocity, humidity, and conveyor speed are continuously adjusted via PID feedback loops. Total bake time is between 85 and 105 seconds. Baked sheets are discharged onto a mesh cooling belt, where ambient forced air coolers reduce sheet temperature to below 30 degrees Celsius within 90 seconds. Cooling is followed by longitudinal slitting. Circular slitting blades mounted on adjustable shafts divide the wide wafer sheet into narrow, uniform ribbons matching the final roll width. Slitting accuracy is maintained using laser alignment sensors. Each ribbon is immediately guided into a spiral roll-forming station equipped with a rotating mandrel. A servo-controlled drum pulls the ribbon over the mandrel, while controlled tension and heat reactivation of the dough surface allows the strip to roll into a rigid, cylindrical shell. Formed rolls are passed through a stabilization tunnel maintained at 65-75 degrees Celsius with low humidity to fully set their shape. Rolls are discharged onto a buffer conveyor which feeds into the cream filling station. In parallel, the cream filling is prepared from sugar, hydrogenated vegetable oil, milk solids, lecithin, artificial flavor, and small amounts of stabilizers. Ingredients are batch loaded into a jacketed mixing vessel with shear blades rotating at 1400 and 1600 RPM. Oil is added slowly to prevent separation, and the entire mixture is heated to 45-48 degrees Celsius. Mixing continues for 10 to 15 minutes until a homogeneous emulsion is achieved. The finished cream is transferred through insulated stainless steel pipes to pressurized holding tanks. agitators maintain cream fluidity and prevent phase separation. The filling is then pumped to multiple servo-driven depositors aligned with each lane of the wafer roll conveyor. Each nozzle delivers a calibrated cream column into the core of each roll, with filling weights accurate to plus 0.2 grams. The nozzle retracts dynamically during deposit to ensure central cream alignment and full core penetration. Cream-filled rolls pass through a secondary cooling tunnel set to 10 degrees Celsius for 60 seconds to solidify the filling. Thermal imaging sensors confirm internal stabilization before exiting. At this stage, each roll is individually scanned for dimensional conformity, surface defects, and fill anomalies. Rolls not meeting target criteria for weight, symmetry, or visible cream containment are diverted via pneumatic actuators into separate waste chutes. Approved rolls proceed to flow wrapping. Individual rolls are aligned using vibratory feeders and grouped into packaging sets based on SKU configuration. Film is dispensed from reels and formed into tubes by collaring mechanisms. Horizontal seal jaws apply pressure and heat at 135-145 degrees Celsius for 0.3 to 0.5 seconds to close the ends and seal the longitudinal seam. Nitrogen gas is flushed into the package before sealing to displace oxygen and slow fat oxidation. Each wrapper is printed with batch code, timestamp, and best before date using thermal inkjet printers synchronized with the machine cycle. Wrapped products are conveyed to a cartoning unit, where robotic arms pick and place the flow-wrapped units into pre-formed cartons. Cartons are constructed from pre-creased flat blanks that are folded and glued using hot melt adhesive. Carton fill conformation is performed using weight sensors and machine vision. Completed cartons are sealed, labeled, and aggregated into corrugated shipper boxes. Each shipper box is barcoded for traceability and palletized in accordance with standard load configurations. Palletized loads are stretch-wrapped and transferred to climate-controlled warehouse storage. Storage areas maintain relative humidity below 60% and ambient temperature between 18 and 22 degrees Celsius to prevent wafer degradation and cream migration. Inventory turnover is managed via FIFO principles enforced by warehouse management software, which integrates with factory MES and ERP systems for batch tracking. Process validation occurs every production shift. Operators test dough rheology, sheet thickness, baking curve, moisture content, cream viscosity, deposit weight, roll hardness, and package seal integrity. Data is recorded in the batch record along with any machine adjustments or anomalies. All critical control points, including cream deposit temperature, bake time, and packaging seal strength, are electronically logged and must fall within specification limits or trigger corrective action. Cleaning in place procedures are scheduled every 8 to 12 hours. Cream lines are flushed with heated water, followed by alkaline detergent, acid rinse, and sterile water rinse. Wafer production lines use dry cleaning methods for rollers and belts, followed by compressed air cleaning and manual wipe down of forming mandrels. Swab testing is used to verify microbial cleanliness, and ATP bioluminescence testing is used to assess organic residue. Production yield is calculated by comparing in-feed material weight to packaged product weight, adjusted for expected waste. All off-spec rolls, excess cream, and packaging rejects are weighed and categorized into waste type. Cream residue is routed into closed collection tanks for food waste processing, while wafer rejects are disposed of according to facility-specific food waste handling protocols. All mechanical systems, mixers, sheeters, formers, depositors, and sealers are maintained under a scheduled preventive maintenance program. Bearings, blades, nozzles, and conveyors are inspected and replaced based on run hours. PLC logic controllers monitor machine health via vibration sensors, motor load curves, and cycle time deviation analysis. Batch documentation includes raw material lot numbers, machine settings, environmental conditions, operator identification, in-process test results, and any deviations from standard operating conditions. These records are archived digitally and are subject to internal audits, third-party verification, and regulatory inspection. Full traceability is retained for every unit produced. Nutella B-ready consists of 3 major components manufactured on synchronized but separate production lines: a wafer shell, a Nutella filling, and the final packaging. Each component is produced under tightly controlled parameters using fully automated equipment integrated into a high-throughput, continuous processing line. The outer shell is made from a low-moisture, wheat-based dough formulated to bake into a crisp, blister-free wafer. The dough formulation begins with dosing refined wheat flour, sugar, salt, leavening agents, and a blend of plant-based fats into an enclosed paddle mixer. Dry ingredients are dispensed from silo systems into individual weigh hoppers with accuracy to within plus 0.1%. Liquids, including water and emulsifiers, are metered from heated tanks using flow meters. The mixer operates at multiple speeds for uniform hydration and structural development. Once the dough reaches the required consistency, typically between 22% and 25% moisture content, it is discharged via bottom gate valves into an auger conveyor leading to the forming line. The dough passes through a series of lamination rollers where it is flattened to a precise thickness of 1.4 millimeters. Differential speed control across rollers prevents tearing and ensures uniform surface tension. Edge trimmings are continuously recycled to minimize waste and maintain dimensional consistency. The laminated sheet enters a rotary molding system. This consists of a rotating die roller with cavity molds shaped to match the profile of the Nutella B-ready shell. The dough is pressed into the molds using counter-rotating pressure rollers. An adjustable doctor blade removes excess dough from the roller surface. Molded wafers are transferred via a vacuum pickup system to a baking mesh conveyor, which passes through a tunnel oven with multiple independently controlled zones. The oven zones maintain specific temperature gradients between 180 degrees and 220 degrees, optimized for water evaporation, structural hardening, and color development. Each zone's airflow is modulated by variable frequency drive fans to control browning without burning. Baking duration is typically between 80 and 110 seconds. Thermocouples and moisture sensors measure real-time parameters. Upon exiting, wafers are cooled in line using ambient air-blown axial fans, reducing temperature to under 30 degrees Celsius within 2 minutes. Simultaneously, Nutella filling is prepared in a separate processing room using a continuous mixing system. Ingredients including refined sugar, vegetable oil, skimmed milk powder, cocoa, and hazelnut paste are dosed using mass flow meters and pneumatic transfer lines. Mixing occurs in a double-jacketed emulsification vessel with counter-rotating impellers operating at 800 to 1200 RPM. The temperature is held between 40 degrees and 45 degrees C during mixing to maintain fluidity and preserve emulsion stability. The finished Nutella filling is pumped through heat-insulated stainless steel piping into buffer tanks connected to multi-head depositor units. These depositors are aligned with the conveyor lanes carrying the pre-formed wafer shells. Each depositor nozzle dispenses a precise amount of filling, usually between 12 and 16 grams, into the hollow cavity of each wafer. Fill weight is monitored using inline load sensors that reject any units outside the tolerance band of plus 0.3 grams. To prevent air entrapment during deposition, the filling nozzle retracts during injection at a synchronized rate, matching the filling viscosity and back pressure. Cream flow is assisted by low-pressure nitrogen to maintain a consistent stream and eliminate pulsing. After filling, each shell passes through a cooling tunnel maintained at 10 to 12 degrees to solidify the fat phase of the filling and prevent oil migration into the wafer wall. Following cooling, a pre-molded wafer lid is applied to seal each filled shell. These lids are formed from the same dough and are baked separately on a synchronized rotary system. A robotic arm equipped with vacuum suction cups picks and places each lid onto the open cavity. An edible adhesive compound, typically a glucose-based syrup, is applied to the perimeter edge to create a bond. Pressure rollers compress the lid and base together for mechanical adhesion. After sealing, each unit passes through a mechanical inspection station. High-speed cameras and laser profilometers verify shell integrity, alignment, lid placement, and overall dimensions. Any product with cracks, offset seals, or excessive height deviation is automatically rejected via pneumatic diverter arms. Approved units move into the packaging preparation line. Packaging begins with flow wrapping. Individual Nutella B-ready units are spaced on timing belts and fed into the wrapping machine using servo motor controlled pushers. Wrapping film is fed from a roll and formed around each unit via a forming collar. Horizontal and vertical seals are applied using heated sealing jaws that operate at 130 degrees, 145 degrees. Modified atmosphere packaging is implemented via nitrogen gas injection prior to sealing to displace oxygen and extend shelf life. Each flow-wrapped unit is scanned by barcode readers and printed with date codes and traceability numbers using thermal inkjet printers. Units are counted and grouped into sets of 6 or more, depending on market configuration. Grouping is performed using star wheel collators, which align the units into rows for secondary packaging. Secondary packaging uses flat fold cartons erected via vacuum cup pick-and-place systems. Hot melt glue is applied via nozzles to predefined folding flaps, which are pressed closed by mechanical arms. Each carton receives printed labels containing product name, nutritional data, batch code, allergen information, and certification marks. Cartons are weighed for content verification and stacked into larger corrugated shipping boxes using layer-forming robotic packers. Palletizing is performed by 6-axis robotic arms with end effectors designed to grip multiple boxes per cycle. Standard Euro or industrial pallets are loaded based on customer logistics requirements. Pallet patterns are configured to ensure structural stability and airflow clearance. Once loaded, pallets are wrapped using stretch film machines that apply 250% pre-stretched film to secure load integrity during transit. Each pallet is tagged with a pallet license plate containing full production metadata, including line number, production date, shift code, storage conditions, and destination route. Pallets are moved into finished goods, storage warehouses with temperature and humidity control systems set to maintain between 18 degrees Celsius and 20 degrees, with relative humidity under 60%. Pallet positions are recorded using warehouse management systems with RFID scanners and barcode tracking. Throughout the production process, all inputs, outputs, and in-process conditions are monitored by a centralized SCADA system. Parameters such as oven temperature, mixer torque, depositor cycle counts, wrapping seal integrity, and product rejection rates are logged and archived. Alerts are generated automatically for any deviation outside programmed thresholds. Operators access these systems via HMI touchscreens placed at each station. Sanitation protocols are applied on a rotating schedule. Dough preparation lines are cleaned with dry brushing, followed by ethanol-based surface wipes. Cream handling equipment undergoes full CIP cycles involving alkaline wash, acid rinse, and sterile water flush, validated with conductivity and pH sensors. Wrapping and cartoning stations are cleaned with compressed air, brush downs, and isopropyl surface sanitizers. Swab samples are taken post-cleaning and tested for microbial load. Preventive maintenance is performed weekly on all forming dies, depositor heads, conveyor bearings, and sealing modules. Wear components are replaced based on run-hour tracking. Calibration is conducted daily on dosing equipment, weighing scales, and thermocouples. All calibration records are maintained in compliance with regulatory documentation standards. Product testing occurs hourly. Samples are collected from each production lane and evaluated for weight, length, height, filling content, shell texture, seal strength, and packaging tightness. Sensory analysis includes bite resistance, shell-to-filling ratio, and flavor consistency. Non-conforming samples trigger root cause investigations documented in deviation reports. The entire Nutella B-ready manufacturing process is standardized to allow for duplication across multiple production facilities with identical output quality. Parameters are optimized to prevent moisture migration, mechanical breakage, and oil separation, which are common defects in filled wafer-based snack formats. Final product shelf life is tested under accelerated and ambient conditions to verify packaging efficacy. Chips Ahoy. Cookie manufacturing begins with bulk ingredient handling systems that store raw materials in separate silos or intermediate bins under controlled conditions. Low moisture, fine milled wheat flour is pneumatically conveyed from outdoor silos into batch weigh hoppers located above the main mixing area. Granulated sugar, brown sugar, cocoa solids, salt, and baking soda are stored in indoor silos or gravity-fed bins and fed into weigh stations using screw feeders with plus 0.1% dosing precision. Vegetable shortening and liquid invert sugar are stored in stainless steel jacketed tanks with continuous recirculation to prevent phase separation. The shortening is heated to maintain fluidity at 45 to 50 degrees Celsius, and the invert sugar is pumped at a constant rate through positive displacement pumps. All liquid and dry ingredients are tracked using an integrated batching control system that verifies real-time mass flow and batch integrity using load cells and flow meters. Each batch is loaded into a planetary batch mixer with a dual paddle agitator system. Mixing follows a 3-stage time-controlled sequence. First, creaming of shortening and sugars is performed for 3 to 4 minutes at low speed. Next, flour and leavening agents are incorporated at medium speed for an additional 3 minutes. Finally, the mixture is scraped down and mixed on high speed for 1 to 2 minutes until a homogeneous dough with uniform texture and target moisture content of 18 to 20% is achieved. Temperature sensors monitor the dough throughout mixing to ensure it remains within the 20 to 24 degrees CC range. Overheating is prevented by jacketed cooling systems circulating chilled glycol solution. Once the dough is fully mixed, it is discharged into a stainless steel hopper that feeds a cookie depositor via auger conveyors. Before entering the depositor, chocolate chips are metered into the dough using volumetric feeders to achieve a distribution ratio of approximately 20% by weight. The cookie depositor uses servo-controlled pistons to extrude uniform dough portions directly onto a continuously moving Teflon-coated oven band. Deposit weight per cookie is calibrated to between 18 and 21 grams, depending on SKU. Deposited dough pieces are spaced using optical sensors to maintain consistent center-to-center distance and allow for uniform spread during baking. Each dough piece is flattened slightly by a roller to control shape retention. The baking oven is a hybrid convection and radiant tunnel oven with multiple independently controlled heating zones. Total bake time is typically between 8 and 11 minutes. The oven band runs at a set speed that is continuously adjusted by a PID controller based on real-time surface temperature and humidity readings. Oven zone temperatures range from 160 degrees Celsius in early zones to up to 210 degrees Celsius in final zones to ensure progressive starch gelatinization, moisture evaporation, Maillard reaction, and fat migration. Cookies are monitored during baking using infrared pyrometers that measure surface temperature. Steam injection systems in early oven zones are optionally used to control surface moisture and prevent excessive cracking. Exhaust fans in later zones remove excess humidity and volatile compounds. By the time cookies exit the oven, internal moisture content is reduced to between 3 and 5%, ensuring shelf-stable texture and microbial safety. Upon exiting the oven, cookies are transferred onto a wire mesh cooling conveyor system. Ambient air is directed from below and above the belt using axial fans to achieve uniform cooling to under 30 degrees Celsius in less than 3 minutes. Sensors at the end of the cooling belt check surface temperature before transferring cookies to the inspection area. Conveyor vibrations are minimized to prevent cookie breakage during transfer. Each cookie passes under a vision inspection system equipped with high-resolution cameras and infrared lighting. Software algorithms evaluate cookie shape, surface cracking, chip dispersion, color uniformity, and diameter tolerance. Any cookies failing to meet visual standards are rejected using high-speed air jets. All rejected cookies are weighed, logged, and diverted to waste bins for offline handling. Approved cookies move to the packaging station via a system of vibratory conveyors that align and group the cookies into required configurations. For multi-pack packaging, cookies are grouped into stacks using rotary collators and staged for wrapping. Individual flow packs are created using horizontal form-fill-seal machines. Film is pulled from rolls, shaped around each cookie group, and sealed using heated crimp jaws operating at 130 to 150 degrees Celsius. Modified atmosphere packaging may be used with nitrogen flushing to reduce oxygen and delay lipid oxidation. Each wrapped package receives a printed date code, batch code, and line identification number using thermal inkjet printers synchronized with the conveyor belt. Packages are weighed on inline check weighers with rejection arms for any unit falling outside of mass tolerances. Wrapped units are inserted into cartons using robotic pick-and-place arms with vacuum grippers. Cartons are sealed with hot melt glue at 165 degrees Celsius and pressed under controlled pressure to ensure full adhesion. Secondary packaging lines aggregate cartons into shipping cases. Cases are erected from flat blanks, filled automatically, and closed with either glue or tape depending on distribution requirements. Completed cases are printed with pallet codes, production timestamps, and destination routing labels. Automated guided vehicles, AGVs, or roller conveyors transfer cases to palletizers. Palletizing robots layer the cases using defined stacking patterns optimized for pallet stability and load efficiency. Each pallet is scanned for completeness using weight and barcode validation before being stretch wrapped in polyethylene film at 250% pre-stretch. Wrapped pallets are moved to finished goods warehouses with controlled temperature and humidity, typically 18 to 20 degrees C and 50 to 60% RH. Every stage of the process is controlled and logged using a manufacturing execution system, MES. Batch records include ingredient lot numbers, mixing parameters, bake curves, oven temperatures, deposition weights, packaging counts, inspection rejections, and finished product quantities. Quality control technicians collect hourly samples to perform destructive and non-destructive testing on cookies. Tests include diameter measurement with calipers, moisture analysis via moisture, analyzer, texture profile analysis using 3-point bending rigs, and chip count per cookie via manual visual audit. Organoleptic tests include bite resistance, sweetness intensity, and flavor profiling under controlled conditions. Data is stored electronically and checked against specification ranges defined in the product specification documents. Production lines are cleaned on a rotating schedule. Between batches, dry cleaning is performed using brushes and vacuum systems to remove flour dust and crumbs. At daily intervals, equipment is disassembled and sanitized using foaming alkaline cleaners, followed by water rinses and food-safe sanitizers. Chocolate lines undergo specialized cleaning to prevent fat bloom and cross-contamination. Allergen control zones are enforced through physical separation of lines, color-coded tools, and allergen-specific cleaning validations. Swab tests for protein residues are performed on high-contact surfaces after each cleaning cycle. If any allergen residue exceeds the defined limit, cleaning is repeated and verified before production resumes. Downtime events such as depositor jams, film feed interruptions, or oven temperature deviations are tracked via the line control system. Operators record the event time, cause, and corrective actions. Line productivity is measured using overall equipment effectiveness (OEE) metrics, including availability, performance, and quality yield. Preventive maintenance on mixers, ovens, conveyors, depositors, and packaging machines is scheduled based on runtime hours. Critical components such as servo motors, bearings, seal jaws, and roller chains are monitored for vibration and thermal performance. Spare parts inventory is maintained in real time using a computerized maintenance management system, CMMS. Finished product samples are retained from each batch for shelf life testing. These samples are stored under accelerated and ambient conditions and tested at intervals for texture degradation, moisture migration, lipid oxidation, and packaging integrity. Results are used to confirm product expiration dates and to evaluate packaging material performance. All operations conform to global food safety standards such as GFSI benchmarking and are subject to internal audits and third-party certification. Traceability systems allow for immediate upstream and downstream tracking of all product components within minutes of any query. Any deviations from process controls trigger root cause analysis under a corrective and preventive action (CAPA) protocol. McDonald's hamburgers begin with bulk shipments of beef trimmings delivered to centralized processing facilities where the meat is unloaded from refrigerated trucks into chilled receiving bays held between 0 and 4 degrees Celsius. Each lot is inspected visually and mechanically with camera-based optical sensors and fat analysis probes verifying color, lean content, and moisture levels. Trimmings are sorted by lean to fat ratio to match McDonald's specification for finished patties, typically between 78 and 82% lean. The selected beef portions are conveyed into stainless steel grinding machines fitted with cold jacketed chambers to prevent temperature rise during processing. The grinding heads use fine perforated plates with rotary blades that reduce the muscle tissue into uniform granules of approximately 3-4 micra in diameter. The ground beef is discharged into a horizontal ribbon blender, where any remaining lean to fat variation is equalized through slow speed agitation for 1.5 to 3 minutes. The blended ground beef is then conveyed to an automated portioning and forming line. This system uses volumetric piston feeders that inject exact quantities of meat into stainless steel molds arranged on a rotating turret. Molds are machined to tight tolerances to produce consistent diameter and thickness. Each formed patty is ejected onto a conveyor belt and transferred through a vision-based quality control station that checks for shape deviation, edge defects, and uniformity. Immediately after forming, the patties pass through a metal detector calibrated to identify ferrous and non-ferrous contaminants as small as 1 mm in diameter. Acceptable patties are then laid in single layers on perforated stainless steel trays and enter a spiral blast freezer with multi-tiered conveyor belts. Air circulated at 35 degrees Celsius freezes the patties within 6 to 10 minutes, preserving cell structure and preventing microbial growth. Once frozen solid, the patties are robotically stacked into polylined corrugated cartons. Each carton receives a thermal inkjet printout of lot number, facility ID, timestamp, and storage instructions. Cartons are sealed, palletized using 4-way interlocking stacking, wrapped in low-density polyethylene film, and stored in warehouse freezers at 20 degrees Celsius. Pallets are tracked by barcode scanning and integrated into the distribution center's inventory management system. Frozen patties are shipped via insulated trucks equipped with temperature loggers to McDonald's regional distribution hubs. There, they are sorted according to store demand forecasts and loaded onto outbound trucks delivering to individual restaurants. On arrival, each restaurant receives its palletized frozen inventory, which is stored in walk-in freezers held at 18 degrees Celsius or below. During service, frozen patties are manually loaded into refrigerated holding drawers set to 1 to 4 degrees Celsius. From there, they are transferred to a double-sided clamshell grill with heated top and bottom platens. The grill uses preset cooking profiles with digitally regulated temperature zones and timer controls to ensure cooking consistency. The platens press down with calibrated force to ensure uniform contact and searing across the entire surface. Cooking temperatures are typically set between 218 and 232 degrees Celsius. Contact grilling sears both sides simultaneously, allowing internal temperatures to reach a minimum of 69 degrees Celsius within 38 to 45 seconds, depending on patty thickness. Internal thermocouples and surface heat sensors validate cooking cycle completion. Cooked patties are transferred to a heated holding cabinet set to 65 degrees Celsius with a maximum residence time of 15 minutes. Hamburger buns are delivered from third-party commercial bakeries in sealed plastic bags, stored at ambient room temperature. Each bun is pre-sliced horizontally and stored in dry shelving units. At the point of order, buns are transferred into a bun toasting system that uses a pair of vertically aligned platen heaters. The interior face of each bun half is pressed briefly against a 290 Celsius hot surface for 8 to 12 seconds, resulting in light browning and moisture barrier formation. Buns are then transferred to the assembly line, where a standardized sequence of condiments is applied. Condiment stations are calibrated to dispense fixed volumes per activation. Ketchup and mustard dispensers are gravity-fed with pneumatic pumps, delivering approximately 2.2 grams of ketchup and 1.5 grams of mustard per burger. Diced onions are stored in chilled bins and applied using pre-measured scoops to maintain serving consistency. Pickles are stored in brine within covered cold pans and dispensed using tongs or measured forks, with each sandwich receiving 2 pickle slices. If the burger includes cheese, processed cheese slices are stored in a heated drawer at 30 to 35 degrees Celsius to retain pliability and avoid breakage. A single slice is placed directly on the hot patty to allow softening from residual surface heat. Cheese is never reheated directly to avoid oil separation or rubbery texture. The patty is placed on the heel of the bun, aligning it center to edge within a maximum deviation of 5 millimeters. The crown of the bun, bearing condiments and toppings, is pressed onto the patty with light manual pressure. The assembled burger is placed into a food-grade cardboard clamshell labeled with SKU and timestamp. The product is immediately transferred to a chute or pickup station, depending on whether the order is dine-in, takeout, or drive-through. All ingredients and subsystems are governed by an electronic kitchen management system. This system tracks inventory movements, cooking cycles, and holding times in real time. The grill communicates with the central controller via embedded microcontrollers. Alerts are generated when product remains on the grill or in the holding unit beyond preset time limits. Cleaning and maintenance schedules are defined per equipment type. The grill surfaces are cleaned with non-abrasive pads between cycles, with a full disassembly and detergent cleaning conducted during low-volume hours. Bun toasters, condiment dispensers, and heated drawers are sanitized using food-safe cleaners at daily intervals, logged manually in inspection sheets. Cooking oil from other station components, such as fryers, is not used in hamburger production. However, grill grease is collected through internal drainage channels and directed into a sealed grease trap located below the cooking surface. These traps are emptied by third-party disposal services following regulatory standards for food service waste. Employee actions in burger assembly are standardized through training modules and visual process flow guides posted at the station. Assembly steps, ingredient order, and portion control are not subject to personal variation. A deviation beyond defined tolerance, for example, 3 pickles instead of 2, would be logged as an error in the station's quality control record. Ingredient restocking occurs during shift change or low traffic periods. Cheese, onions, buns, condiments, and patties are replenished by staff using designated procedures to ensure oldest inventory is used first. Expiry times are marked on all trays using color-coded labels or dry erase markers based on current health code regulations. The overall process from freezer to assembled burger takes approximately 3 minutes, with cooking accounting for less than half that duration. Each burger conforms to predefined standards for temperature, weight, ingredient distribution, and presentation. Random audits by shift managers and corporate inspectors validate conformity, and deviations are recorded in digital quality logs. At the end of service, all remaining patties in the holding cabinet are discarded if they exceed the 15-minute maximum hold window. Waste is recorded for internal tracking, and excess is analysed during shift reports to optimise future grill loading decisions. Allergen control protocols are in place for products containing cheese or bun components processed in facilities that handle wheat, soy, or dairy. Equipment used for allergen-containing items is cleaned using verified procedures before cross-contact sensitive menu items are prepared. Burger King hamburgers begin at industrial-scale meat processing facilities, where fresh beef trimmings are delivered in vacuum-sealed containers maintained below 4 degrees Celsius. The trimmings are offloaded into chilled receiving areas equipped with stainless steel conveyors and holding bins. The bins feed directly into grinders fitted with cutting plates calibrated to a precise perforation diameter between 3.2 and 4.8 millimeters. The grinding process is conducted under controlled temperatures to prevent protein denaturation and inhibit microbial growth. The ground beef is transported via enclosed auger systems into horizontal ribbon blenders that homogenize the mixture to a target lean-to-fat ratio of approximately 80-20. Blending continues for 90 to 120 seconds at low RPM to avoid heat buildup. Each batch is sampled for moisture content, fat dispersion, and microbial contamination. No seasonings, fillers, preservatives, or additives are introduced. Quality-approved batches are routed directly to the forming line. The forming process uses hydraulic form and eject systems with rotary dies that compress the meat into circular patties of fixed mass, diameter, and thickness. Optical sensors monitor patty integrity, checking for cracks, underfilled molds, or edge defects. Formed patties are placed onto poly-coated food-grade conveyor belts and immediately pass through a metal detection tunnel calibrated to detect ferrous and non-ferrous contaminants as small as 1.0 millimeter. Patties then enter a spiral freezer where air chilled to 35 degrees Celsius circulates at high velocity to harden the product within 7 to 10 minutes. Rapid freezing limits ice crystal growth and preserves cell structure. Upon exit, frozen patties are automatically stacked in counted layers into polyethylene-lined cartons. Each carton is sealed, labeled with a unique batch code, production timestamp, and storage requirements, then palletized and transferred to cold storage held at 20 degrees Celsius or lower. Frozen patties are shipped in refrigerated trailers equipped with continuous temperature logging devices that provide data on transit conditions. At Burger King distribution centers, incoming pallets are scanned into inventory and stored in walk-in freezers. Orders are fulfilled based on store demand algorithms, with frozen patties delivered to individual restaurants on a rotational inventory system that ensures first in, first out usage. At the restaurant level, frozen patties are stored in low temperature freezers until transferred to refrigerated drawers for same-day cooking. Each drawer maintains internal temperatures between 1 and 4 degrees Celsius. Restaurant operations follow a grill-to-order or batch preparation method depending on volume. Cooking is done using a proprietary gas-fired broiler system equipped with a continuous stainless steel chain conveyor that transports raw patties through a tunnel with overhead and under-fired direct flame burners. Each patty is manually placed onto the moving broiler belt, which advances at a fixed speed preset according to patty thickness and desired internal temperature. As the patty enters the broiler tunnel, infrared sensors verify burner ignition and temperature stability. The open flame directly contacts the surface of the patty, inducing a Maillard reaction that produces characteristic grill marks and seared flavor. Simultaneously, moisture is driven out of the meat surface, concentrating the flavor and forming a firm exterior crust. The broiler conveyor moves at a calibrated pace, typically between 2.5 to 3.5 minutes per pass, depending on the product type. Internal temperatures of patties are monitored via embedded thermocouples in test units during hourly quality assurance checks. Each patty must achieve an internal temperature of at least 71 degrees Celsius before being passed to the holding area. The broiler is equipped with grease drainage systems that collect rendered fat into heat-resistant trays, which are emptied and cleaned daily. Cooked patties are deposited onto a stainless steel chute that guides them into heated holding trays. These trays are equipped with radiant heat elements that maintain surface temperatures between 60 and 65 degrees Celsius. A digital timer tracks how long each tray has been loaded. Cooked patties are held for a maximum of 10 minutes before being discarded to maintain texture and taste consistency. Each tray is labeled with a batch code and timestamp for traceability. While patties are cooking, buns are processed through a vertical bun toaster equipped with conveyor-style platen heaters. Buns are stored at room temperature in sealed bags until loaded into the toaster's gravity-fed chute. Each bun is sliced horizontally, and the interior face is pressed against a heated platen set to 293 degrees Celsius for 9 to 11 seconds, producing a lightly toasted surface that provides moisture resistance and structural stability during sandwich assembly. At the assembly station, buns are transferred to stainless steel prep surfaces. Condiments are applied using calibrated squeeze bottles or piston-driven dispensers. Mayonnaise, ketchup, and mustard volumes are controlled to within 0.2 gram tolerance per sandwich. Pre-chopped lettuce is stored in refrigerated bins held at 1 to 4 degrees Celsius and portioned with measured scoops. Sliced tomatoes are machine cut off-site to uniform thickness and stored in cold bins. Pickles are pre-sliced, stored in brine, and dispensed manually or by volume-controlled tongs. Onion slices are separated into rings and stored dry in chilled compartments. Cheese slices, individually separated by interleaving sheets, are held in humidity-controlled drawers and applied manually to hot patties. Melting begins on contact due to retained surface heat from the broiler. In multi-patty configurations, cheese is placed between layers to bind them together. Burger crowns are pressed gently onto the sandwich to complete assembly. Each finished burger is placed into a pre-folded paper wrap or cardboard clamshell, depending on store packaging configuration. Clamshells are pre-loaded into gravity-fed dispensers and labeled with SKU identifiers. Assembly staff insert each item into its respective packaging within 10 seconds of completion to reduce heat loss. Packaged burgers are queued on heat-retaining stainless steel chutes until collected by frontline staff or drive-through personnel. All steps of production, from raw patty to finished burger, are logged via point-of-sale integrated kitchen management systems. These systems track timestamps for cook cycles, holding durations, and ingredient usage. Broiler temperatures, toaster settings, and holding bin temperatures are verified hourly against digital readouts and documented in quality assurance logs. Ingredient rotation follows a strict first in, first out schedule. Bins for lettuce, tomato, and onions are marked with timestamps. Condiment cartridges are replaced every 4 hours. Cheese drawers are sanitized every 4 hours or upon visible residue. Packaging materials are stored in dry areas above floor level and inspected daily for contamination or damage. Cleaning procedures for the broiler include nightly shutdown and disassembly of the chain, flame shields, and drip trays. Components are soaked in degreasing solution, brushed with food-safe abrasives, rinsed with potable water, and reassembled before morning operations. Bun toasters are wiped down between shifts and deep cleaned daily. Stainless steel prep surfaces are sanitized using quaternary ammonium-based solutions between each menu changeover. Waste patties beyond holding limits are recorded and disposed of according to local food safety regulations. Waste logs categorized by reason: overcooked, expired holding time, or off-spec grill temperature. Daily waste volumes are analyzed against hourly demand forecasts to optimize future batch sizes and reduce discard rates. Every element of the system is engineered for reproducibility. Conveyor speed, burner placement, heating element calibration, and ingredient flow are all configured to produce identical results across every store. Burger King's operational procedures specify not only the quantity of each topping, but the order of application, spacing, and placement centering to reduce variability. Thermal cameras and real-time temperature logging are used in some test markets to improve process control. Wendy's hamburgers begin with the processing of fresh, never frozen beef. Whole muscle cuts are delivered to regional patty processing facilities in refrigerated containers held between 0 and 4 degrees Celsius. These cuts are trimmed of excess fat and connective tissue by mechanical blade systems equipped with thickness sensors and cutting guides to standardize input material. The trimmed beef is passed through fine grinding plates with perforation diameters ranging from 3.5 to 5.0 millimeters to produce uniform ground meat. The ground beef is loaded into stainless steel mixing tanks where the lean to fat ratio is balanced to approximately 80.20 using real-time fat analysis sensors and automated auger feeding systems. No preservatives, fillers, or additives are introduced. The blend is mixed gently under chilled conditions to prevent protein degradation and to retain water binding capacity. The mixture is tested for microbial content, temperature, and compositional accuracy before advancing. Patties are formed using hydraulic forming machines with square dies, giving Wendy's burgers their distinctive shape. Each mold is calibrated for precise weight and thickness, typically 113 to 170 grams, depending on the product line. Formed patties are transferred to a conveyor where machine vision systems inspect for edge defects, cracks, or inconsistencies in surface texture. Acceptable patties are placed into single-layer, vacuum-sealed packaging and labeled with production time, lot number, and expiration date. Packaged patties are transported to restaurant locations via refrigerated trucks maintained below 4 degrees Celsius. Upon arrival, the patties are stored in walk-in refrigerators with air circulation systems designed to maintain uniform temperatures and humidity. The storage area uses FIFO inventory rotation, tracked by internal labeling systems that log delivery and use dates. Patties are removed from cold storage and transferred to a flat-top grill for cooking. The grill is made of polished steel and heated by independently controlled heating zones, maintained at temperatures between 218 and 246 degrees Celsius. Cooking surfaces are checked for temperature consistency using surface thermometers before each service period. No oil is added to the grill surface, as the beef renders its own fat during cooking. Raw patties are placed directly on the hot surface and pressed with a weighted spatula to ensure even contact and browning. The searing process forms a crust that locks in juices and enhances flavor through Maillard reaction. Internal patty temperature is monitored using digital thermometers to ensure a minimum internal temperature of 71 degrees Celsius is reached. Cooking time ranges from 3 to 4.5 minutes per side, depending on patty thickness and grill load. Patties are flipped once during cooking using flat-edge spatulas to maintain structural integrity. Drippings are channeled into built-in grease traps that are emptied and cleaned daily. Finished patties are transferred directly to a heated holding tray set to maintain product between 60 and 65 degrees Celsius. Holding time is limited to 5 minutes to ensure texture and flavor integrity. Burger buns are delivered from certified commercial bakeries, stored in ambient conditions in dry storage areas, and used within labeled shelf life. Buns are sliced in-store using serrated rotary cutters attached to prep tables. Each half is toasted on a separate bun toaster fitted with heated platens that reach 285 to 295 degrees Celsius. Toasting duration is controlled to within 0.5 seconds per bun half to ensure uniform color and surface dryness. Toasted buns are transferred to the sandwich assembly station, where standard build sequences are followed. The sandwich station includes dedicated zones for condiments, vegetables, cheese, and protein. Mayonnaise and ketchup are dispensed using piston-based systems with adjustable volume control set to deliver consistent amounts per sandwich. Mustard and other optional sauces are applied manually in measured dollops using portion-controlled utensils. Fresh lettuce is shipped pre-cut and triple washed, stored in refrigerated prep tables between 1 and 4 degrees Celsius. Tomatoes are sliced daily using mechanical slicers to a thickness of 5 millimeters and stored in high humidity containers. Onions are peeled and sliced into rings and portioned by visual estimation or scale weight. Pickles are brined and pre-sliced, dispensed using tongs from refrigerated compartments. Cheese is individually sliced and stored in covered trays within the sandwich station's cold section. A single slice is placed directly onto the hot patty immediately after cooking. The heat from the patty softens the cheese, but does not fully melt it, preserving slice definition. Bacon, if added, is cooked separately on a flat-top griddle and held in warming drawers lined with absorbent paper and heated via low-voltage infrared elements. Assembly order follows strict guidelines. The bottom bun receives sauces and condiments, followed by lettuce, tomato, and onion. The patty is placed on top of vegetables to reduce heat transfer to the bun. Cheese, bacon, and pickles are layered above or below the patty based on product specifications. The crown bun is pressed on top to complete the build. Assembled burgers are wrapped in branded foil wrappers or placed in paperboard containers depending on order type. Wrappers are designed with heat-retaining layers and moisture vents. Burgers are staged in a holding chute or placed directly into order bags. All packaging materials are stored in dry stock rooms and replenished daily. Package weight and sandwich construction are audited periodically for consistency. Restaurant kitchens use an operations management system that logs grill usage, cooking cycles, and holding times. Thermocouple sensors embedded in the grill surface provide live temperature feedback. Digital timers alert staff when patties must be removed or discarded. Each station is monitored for compliance with production procedures via internal checks and periodic inspections. Cleaning schedules are programmed to occur at shift changes and closing. Flat-top grills are scraped after each use and cleaned with food-safe degreaser at the end of each day. Grease traps are emptied, wiped, and sanitized using quaternary ammonium-based disinfectants. Prep surfaces are wiped with single-use sanitizer wipes and tested with ATP swabs for surface cleanliness verification. Unused raw patties at the end of the day are discarded if past time limits. Opened, condiments are sealed and stored in designated cold storage with labeled expiration dates. Open vegetable containers are covered with plastic film and labeled with the date and time of preparation. All leftovers are monitored for spoilage indicators and disposed of if they exceed quality thresholds. Each restaurant uses a real-time inventory and supply tracking system linked to a central database. Usage rates for beef, buns, vegetables, cheese, and condiments are analyzed against sales data. Discrepancies trigger alerts to management and may result in retraining or procedural audits. Ingredient reorders are generated automatically based on projected demand using historical sales averages. Allergen control measures are implemented in burger production through equipment segregation and cleaning protocols. Separate spatulas and prep zones are designated for allergen-free products. Staff receive allergen training and use visual cue systems to avoid cross-contact. Labels indicate allergen presence per local regulatory requirements. Throughout the process, every input is controlled and verified to produce uniform hamburgers across locations. Cooking parameters, ingredient measurements, and build sequences are optimized for speed, consistency, and quality. Final products are subject to visual inspection, temperature checks, and build verification by designated shift managers. Any deviations are logged and addressed through corrective procedures. Dairy Queen ice cream begins with the formulation of a liquid ice cream mix that contains a specific balance of milk solids, butterfat, sweeteners, stabilizers, and emulsifiers, all designed to create a product with a soft serve texture, rich flavor, and the structural integrity to hold shape when dispensed at below freezing temperatures. The process starts with the metering of liquid ingredients into a high-capacity stainless steel mixing tank. Milk, cream, and liquid sweeteners, such as corn syrup, are pumped from refrigerated storage tanks using automated pumps that are controlled through a programmable logic controller system. The precise volumes are determined by batch recipes that are stored digitally and loaded into the mixing unit via operator interface panels. Dry ingredients like skim milk powder, dextrose, and stabilizer emulsifier blends are added through a dry powder feeder positioned over the mixing tank. As the powders are introduced, high-speed impellers and rotor-stator mixers circulate the mixture, dispersing solids uniformly and ensuring the base is homogeneous. This initial mix is agitated continuously for a set period until the solution reaches a uniform temperature and particle distribution. Once mixed, the liquid ice cream base is pumped through a series of inline filters to remove any clumps, undissolved particles, or foreign matter before proceeding to the pasteurization stage. Pasteurization is a critical thermal process that ensures microbiological safety and improves the mix's ability to support uniform freezing and aeration. The base mix is pumped through a plate heat exchanger system, which uses hot water or steam on one side of the stainless steel plates and the ice cream mix on the other. The two fluids never touch, but heat is transferred efficiently across the metal surfaces. The mix is quickly heated to a target temperature, typically around 80 to 85 degrees Celsius, and held at that temperature for a predetermined number of seconds, usually no more than 25, before being rapidly cooled to below 4 degrees Celsius using chilled water or glycol solution in the next section of the exchanger. The rapid heating and cooling prevent unwanted protein denaturation while killing potential pathogens. The chilled, pasteurized mix is then transferred to an aging tank. These tanks are large, insulated stainless steel vessels equipped with slow-speed agitators that maintain gentle circulation without incorporating air. The mix is aged for a minimum of 4 hours often overnight, to allow the fat crystals to partially solidify and the stabilizers and emulsifiers to fully hydrate. This aging process improves body, creaminess, and melt resistance of the final product and ensures a consistent structure when the mix is frozen later. After aging, the liquid mix is pumped into a continuous freezer. This is where the transformation from liquid to frozen soft serve occurs. The continuous freezer is a high-efficiency, jacketed stainless steel cylinder containing a rotating scraper blade assembly and a direct expansion refrigeration jacket filled with ammonia or another refrigerant. As the mix enters the chamber, it is chilled to approximately 6 to 8 degrees Celsius while being whipped rapidly by the rotating blades. This mechanical action accomplishes two things at once. It freezes the water content of the mix into fine ice crystals and incorporates air into the structure to create overrun. Overrun is the term used to describe the volume of air introduced into ice cream, expressed as a percentage of the original mix volume. Dairy Queen soft serve typically has a controlled overrun around 45%, meaning 100 liters of base mix will become 145 liters of finished product. This air is crucial for texture, mouthfeel, and lightness. It is injected through filtered nozzles as the blades churn the mixture. The balance of air and ice must be tightly regulated. Too much air leads to foaminess, while too little creates a heavy, dense product that doesn't dispense smoothly. The frozen, aerated soft serve exits the continuous freezer at a semi-solid state and is transferred immediately into sterile holding tanks or directly into distribution containers, depending on the factory design. In larger operations, the soft serve may be pumped into pre-chilled, bag-in-box containers made of multi-layered, food-safe plastic film that protects the product from light and moisture. Each bag is filled by volume through a no-drip valve, sealed mechanically, labeled with a production code and expiration date, and moved to refrigerated storage. In other systems, the soft serve may be routed into pressurized stainless steel kegs or bulk plastic drums equipped with quick connect couplings for easy installation at the retail dispenser level. These containers are filled in clean rooms under positive pressure airflow to eliminate airborne contamination. The filled containers are immediately stored at sub-zero temperatures in blast freezers or walk-in cold rooms set to maintain the product just below the freezing point without hardening the mix entirely. From here, the frozen product is shipped in refrigerated trucks to the point of sale, typically a retail location equipped with a dedicated soft-serve dispensing machine. These machines are miniaturized versions of the industrial continuous freezer used in the factory. Each machine contains a hopper that holds the soft-serve mix, an auger or scraper blade assembly, and a narrow freezing cylinder cooled by either air or water-based refrigeration systems. When the machine is activated, the product is pulled from the hopper into the freezing cylinder where it undergoes a final freezing and aeration stage. The mix is chilled further to about 9 degrees Celsius while the blades whip it to preserve consistency. When the lever on the dispenser is pulled, the pressurized frozen product is extruded through a specially designed nozzle that imparts the signature spiral swirl to the ice cream as it is dispensed into a cone or cup. Each part of this process, from raw milk to cone, relies on tightly controlled mechanical parameters, time-sensitive transitions, and a closed system design that ensures the finished Dairy Queen soft serve has a consistent texture, smooth pour, and creamy mouthfeel. The cooling cycles, flow rates, agitation speeds, syrup-to-air ratios, and thermal profiles are all digitally monitored at every stage using PLCs, sensors, thermocouples, and SCADA systems. Adjustments are automated to keep the output within strict tolerances. To ensure quality, samples are pulled at multiple points in the process for physical, chemical, and microbiological testing. These include fat content analysis using infrared spectroscopy, overrun verification using displacement methods, viscosity measurement through flow cups or rotational viscometers, and sensory testing by trained tasters who evaluate mouthfeel, melt profile, sweetness, and aftertaste. Sanitation procedures are carried out daily or between batches. All pipes, valves, hoses, and tanks in the mix production system are cleaned in place using automated CIP systems that cycle through pre-rinse, caustic wash, acid rinse, and final sanitizing steps. Soft serve dispensers at the retail level are cleaned manually with specialized brushes and food-safe detergents, followed by complete reassembly and sanitization with hot water flushes to ensure hygiene is maintained without altering the flavor of future batches. Every production batch is traceable by date, time, machine, operator, and ingredient lot, logged in a database that allows for immediate traceback in case of any quality issues. Digital records are kept for regulatory compliance and internal process optimization, helping to refine recipes, extend shelf life, and reduce variability between runs. Bluebell ice cream production begins with the assembly of the ice cream base, which is the liquid foundation used to create every flavor. This base must be smooth, homogeneous, microbially safe, and physically stable throughout the freezing, hardening, and distribution stages. To prepare it, the process starts in a mixing room where stainless steel blending tanks are used to combine raw ingredients such as whole milk, cream, skim milk powder, sugar, corn syrup solids, and stabilizers like guar gum or carrageenan. These ingredients are stored in separate bulk storage silos or tanks at controlled temperatures and are pumped into the mix tank using automated volumetric dosing systems. The control panel interfaces allow operators to select a formula code that precisely dictates the ratios required for each batch. As the ingredients are added to the tank, high shear impellers begin to mix the contents, breaking down solid particles and dispersing fats evenly into the water phase. The temperature is kept in the range of 40 to 50 degrees Celsius to aid solubility and prevent premature thickening. Once mixed into a smooth liquid, the batch is sent through a plate heat exchanger where it is heated rapidly to pasteurization temperatures, usually around 82 to 85 degrees Celsius, and held for 25 to 30 seconds to eliminate any harmful bacteria and extend shelf life. This pasteurization step is monitored using digital sensors that track the flow rate, inlet and outlet temperatures, and holding times. Immediately after pasteurization, the base is cooled just as rapidly by the second half of the heat exchanger using chilled glycol solution or water, dropping the temperature of the mix to around 4 degrees Celsius. This chilled mix is directed into insulated aging tanks where it is gently agitated and held for a minimum of 4 hours. The aging process allows the milk fat to partially crystallize, which improves body and mouthfeel, while stabilizers fully hydrate and develop viscosity. The aging tanks are jacketed and equipped with temperature controllers to ensure the mix stays cold and consistent across the entire volume. From the aging tanks, the base mix is pumped through a filtration unit and into continuous freezers. These freezers are the heart of the transformation process, where liquid mix becomes soft, semi-solid ice cream through a combination of rapid cooling and mechanical aeration. Each freezer consists of a horizontal freezing barrel that's jacketed for refrigeration and fitted with a rotating dasher blade assembly that scrapes the frozen mix from the inside wall while simultaneously blending in air. This air is filtered and injected under pressure to create overrun, the volume of air in the ice cream, which typically ranges from 60 to 90% depending on the product line. The dasher speed and airflow rate are tightly controlled to produce a uniform texture with consistent aeration. As the mix freezes, small ice crystals begin to form, stabilized by the partially solidified fat structure. The blades continue to whip the mixture while keeping the internal temperature around 5 to 7 degrees Celsius, cold enough to form a spoonable texture without fully hardening. At this stage, inclusions like chocolate chips, cookie dough, brownies, caramel swirls, or fruit pieces are introduced. These mix-ins are added using ingredient feeders synchronized with the freezer output. The feeders are auger-based or belt-driven and feed precise quantities of inclusions into the flow stream so that distribution is even but gentle, ensuring that delicate ingredients are not crushed or smeared. As the frozen mix exits the freezer, it is immediately deposited into containers. Bluebell typically uses round paperboard cartons with plastic-coated interiors for ice cream, ranging from pints to half gallons. These cartons are automatically erected from flat stock, positioned on a conveyor belt, and filled via time pressure or piston-based filling heads. The heads are height adjustable and retract as the filling occurs to prevent air pockets or overflow. For varieties with variegates like fudge or fruit syrup, an additional stream is injected into the flow through a ribboning head, creating visible swirls as the carton fills from the bottom up. After filling, a lid is automatically pressed onto the container using pneumatic arms. The sealed containers pass through a rotary or linear check weigher that confirms the net weight is within spec. Underweight or overweight cartons are automatically rejected and sent to a separate path for inspection or rework. Accurate filling is essential not just for consumer expectation, but to ensure uniform freezing in the next step. The sealed containers are then conveyed into a hardening tunnel, which is essentially a long blast freezer where temperatures drop to 30 to 40 degrees Celsius. Inside, high-velocity fans circulate sub-zero air around the cartons, freezing the remaining liquid phase rapidly and reducing the core temperature of the ice cream to below 18 degrees Celsius. This fast hardening process is vital to preserving the fine ice crystal structure created during freezing. The air jets are angled and modulated to provide even exposure and prevent frost buildup or warping of the cartons. The hardened ice cream containers exit the tunnel and move into the packaging area, where they are inkjet printed with date codes, flavor identifiers, and batch numbers. These markings allow full traceability from raw ingredient to final sale. Cartons are grouped into multi-packs using collators and tray packers, then boxed by robotic case packers into corrugated shipping cases. Each case is sealed with tape or hot glue, scanned for correct labeling, and palletized using robotic arms. Pallets are stacked in specific configurations that maximize airflow for cold storage and are wrapped in stretch film to protect against moisture and dust. Finished pallets are transferred to a holding freezer, typically kept between 20 and 25 degrees Celsius, where product is stored until it's loaded into refrigerated trucks. These cold chain logistics are essential to prevent thawing and refreezing, which would cause ice crystal growth and negatively affect texture. Delivery schedules are timed to coordinate with storage capacity and retail demand, ensuring that the product reaches shelves still within the optimal quality window. Every point in the process is monitored through industrial control systems. Pressure sensors, flow meters, thermocouples, and programmable controllers gather real-time data on mix temperatures, freezer speeds, air injection rates, filling volumes, tunnel temperatures, and even ingredient feed rates. This data is reviewed both in real time and after production to analyze batch quality, identify issues, and implement continuous improvement measures. Any batch that deviates from target parameters can be traced back through digital batch logs and ingredient tracking systems, allowing for full quality control. In terms of sanitation, the Bluebell factory uses CIP, clean-in-place, systems on all tanks, lines, and freezers. After each production cycle, a sequence of hot water rinses, alkaline cleaners, acid washes, and final sanitizers is circulated through the system at high velocity. The cycle times temperatures, and chemical concentrations are controlled automatically, and post-cleaning validations are performed using ATP swabs or microbiological plate tests to verify the absence of residue or bacterial growth. Mix-in feeders and surface equipment are cleaned manually between batches, especially when allergens or strong flavorants are involved. The result of all these carefully engineered steps is a product with uniform texture, balanced aeration, clean flavor release, and reliable scoopability straight from the freezer. Whether producing vanilla, cookies and cream, or limited edition seasonal flavors, the factory process remains consistent. Transform a raw dairy mix into a frozen dessert that maintains its integrity from the first pour to the final bite. Ben & Jerry's ice cream begins its journey inside large stainless steel mixing vats where fresh cream, condensed skim milk, and liquid sugars are combined in tightly controlled quantities based on batch-specific recipes, with all ingredients pumped from chilled storage tanks through sanitary stainless steel lines that use flow meters and valve junction boxes to direct each liquid into the blending vessel in the correct sequence, ensuring homogeneity without introducing unwanted turbulence that might destabilize the emulsion forming at the early stages of mixture development. The mixing vats are equipped with high-torque agitators and slow-speed sweep arms that rotate along the inside surfaces of the tank walls, scraping the mixture and pulling ingredients from the periphery into the bulk flow, preventing solids like stabilizers or milk powders from clumping or settling during agitation. While shear heads built into the agitator columns create localized high-energy mixing zones that dissolve particles evenly and allow for a uniform dispersion of all dry and liquid components. Once all base ingredients are integrated, including emulsifiers that help bind the fat and water phases and stabilizers that give the frozen product its structural resilience and slow down melting during consumption, the liquid base is pumped through a plate heat exchanger that rapidly raises the temperature to approximately 82 to 85 degrees Celsius in order to pasteurize the product, which not only destroys pathogenic bacteria, but also activates certain proteins in the milk that contribute to a richer, denser mouthfeel when frozen. After this high-temperature short-time treatment, the base flows immediately into a second section of the heat exchanger, where it is chilled using a closed-loop glycol or ammonia refrigeration circuit that drops the temperature back down to around 4 degrees Celsius in a matter of seconds. And the pasteurized, chilled base is then directed into jacketed aging tanks, which are maintained at low temperatures and fitted with slow, continuous agitators to prevent the separation of fat from the aqueous phase and to allow the stabilizers and emulsifiers to fully hydrate over the course of at least 4 to 8 hours. This aging step is crucial in Ben & Jerry's production process because it prepares the mix to accept not only high levels of air during freezing, but also unusually large and dense inclusions such as brownies, cookie dough chunks, peanut butter swirls, and toffee pieces that would otherwise sink or damage the structure of a weaker base. The aged mix becomes a foundation that can support extreme texture variation without phase separation or flavor loss. Once the aging process is complete, the base is pumped into continuous freezers that serve as the mechanical heart of the frozen transformation. And here, the mix is cooled down to roughly 5 to 7 degrees Celsius while being whipped rapidly inside a horizontal freezing cylinder, where rotating stainless steel blades scrape frozen mix from the walls and simultaneously fold in filtered air through precision-controlled injection valves that regulate the overrun, which is kept deliberately low, around 20 to 30%, compared to typical supermarket ice cream, in order to preserve the ultra-dense, ultra-creamy signature texture that defines Ben & Jerry's. The low overrun means that each scoop contains more ice cream by weight and less air, which makes the freezing process even more critical because dense product holds and transfers thermal energy differently than aerated product. and the refrigeration system must respond in real time to flow rate changes, viscosity spikes due to mix-ins, and fluctuations in pump back pressure, all of which can affect the crystal size and final structure of the ice cream. At this point in the process, flavors and inclusions are introduced using multi-head ingredient feeders, which are synchronized with the flow of frozen base to meter out solid components like brownies, peanut butter cups, or cookie swirls at a controlled rate, using screw conveyors or belt-driven chutes to deliver exact portions into the stream without breaking or over-mixing the inclusions. The goal is to allow each piece to be suspended in the flow with minimal shearing or melting, preserving chunk integrity and creating the variety of texture that Ben & Jerry's is known for. For variegates like fudge ribbons or caramel swirls, the freezer's output is directed into a stream-splitting pipe system where the flow of base ice cream is divided and recombined with injected streams of liquid syrup using spiraled ribboning nozzles that introduce the syrup in twisting arcs, embedding them throughout the product without fully blending them in, and allowing distinct, bold streaks of flavor to appear visually and texturally when the final product is scooped or cut. The combined ice cream and mix-ins flow directly from the freezer head into automated filling stations, where pre-formed pint containers made of wax-lined paperboard or biodegradable composite are delivered via a conveyor, raised into position by a pneumatic lift, and filled from a piston dosing head that controls both the volume and height of the deposit to minimize air pockets while achieving consistent fill weights across thousands of pints per hour. And the filling process includes an overfill compensation stage where a small mound is left at the top to account for post-fill settling and shrinkage during hardening. Once filled, the pints move immediately to a lidding station where domed plastic lids are placed and pressed down using synchronized arms that index precisely with the conveyor's motion, ensuring a tight seal without deforming the container. And each lid is automatically printed with a batch code, timestamp, and flavor identifier using laser or thermal inkjet printers that connect to the plant's centralized batch tracking system, which records every data point from base formulation to final packaging for regulatory compliance and internal quality control. From here, the sealed pints enter a spiral hardening tunnel, which is a vertically stacked freezer that uses high-velocity, ultra-cold air blown at 30 to 40 degrees Celsius to extract heat quickly and reduce the core temperature of each pint to below 20 degrees Celsius within minutes. And this rapid hardening is necessary not just to finalize the freezing process, but also to lock in the structural suspension of inclusions and prevent large ice crystals from forming during storage. The airflow inside the hardening tunnel is controlled by a network of fans and directional baffles that ensure every container receives uniform exposure regardless of its position on the spiral belt. And exit temperature is verified using inline infrared thermometers or embedded probes that signal if any container is under-hardened and needs to be rerouted or rejected. After hardening, the pints are automatically collated into case packers that group them into cardboard boxes or cartons, often 6 or 12 per case, and these cartons are sealed with either tape or hot glue before being labeled with shipping codes and scanned by barcode readers that confirm destination, flavor mix, and inventory count before the cases are stacked by robotic palletizers that arrange cartons into pallet configurations optimized for freezer airflow and shipping stability. Each pallet is stretch wrapped with cold safe film, labeled with a master batch and product manifest, and transferred into deep storage freezers that maintain ambient temperatures between 25 and 30 degrees Celsius to prevent even microscopic temperature fluctuations that could cause texture degradation, especially for pints containing swirl-based variegates that are sensitive to heat migration and sugar inversion if stored improperly. Throughout the factory, process control systems monitor every mechanical and thermal parameter, from ingredient metering to packaging fill rate using SCADA software that aggregates live data from flow meters, temperature probes, mixer speed controllers, and inclusion dispensers. And this information is used both for real-time error detection and long-term quality analysis that allows production managers to fine-tune the sequence of operations and ingredient preparation for future batches. Every component that touches the product is cleaned using CIP clean-in-place systems that route caustic and acidic cleaning solutions through closed-loop pipes, tanks, freezers, and depositors, followed by hot water rinses and sanitizer cycles that are validated through swab tests and chemical residue sensors. And lines are completely stripped and reassembled during allergen changeovers or seasonal flavor transitions to prevent cross-contamination. Ben & Jerry's factory process is designed not just to produce a high-quality ice cream, but to do so with a level of texture complexity and inclusion density that requires more robust mechanics than standard ice cream production. From the strength of pumps used to move mix with dense brownie pieces, to the tolerance of nozzles that must deposit syrup without clogging or overmixing. Each component is selected and calibrated to handle the brand's commitment to chunky, swirly, intensely flavored ice cream with integrity and repeatability.